Imagine making a decision and later discovering that your brain had already made it several seconds earlier. In 2008, neuroscientists at the Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig, Germany, conducted an experiment that surprised even the researchers studying it. Volunteers were placed inside a brain scanner and asked to perform a very simple task. At any moment they chose, they could press one of two buttons. The idea seemed straightforward. Allow people to make a completely spontaneous decision while scientists recorded what was happening inside the brain. But when the researchers analyzed the data, something remarkable appeared. Patterns of activity in certain brain regions revealed which button the participant would press before the participant themselves reported consciously deciding. In some cases, the prediction could be made up to 7 seconds before the person became aware of making the choice. In other words, the brain appeared to begin deciding long before the conscious mind realized anything had happened. This discovery raised a deeply unsettling possibility. What if the moment you feel yourself making a decision is not actually the beginning of the process, but the end of it? What if the subconscious mind has already weighed the options, evaluated past experiences, and prepared the action before the conscious mind even notices that a choice exists? Experiments like these suggest that much of what we experience as deliberate decision-making may actually be the conscious mind catching up to processes that began silently beneath awareness. And yet that strange finding is only one piece of a much larger mystery. In hospitals around the world, neurologists have encountered patients who insist they are completely blind, yet somehow still respond to visual information. In certain cases, individuals with damage to the visual cortex claim they cannot see anything at all in part of their visual field. When objects are placed in that region, they say the space looks completely dark. But when researchers ask them to guess where an object is located or which direction a light is moving, their answers are often correct. Their brains are still processing visual information, guiding their responses with surprising accuracy, even though the patients themselves have no conscious experience of seeing anything. The visual system continues to work quietly beneath awareness, revealing that perception and consciousness are not always the same thing. Hidden systems like these operate inside your mind every moment of your life. Your brain constantly scans the environment, searching for patterns and predicting what will happen next. Long before you consciously react to a situation, networks deep within the brain have already begun evaluating possibilities based on past experiences. This predictive ability is one reason experts can make split-second decisions that appear almost supernatural. Experienced firefighters have reported suddenly ordering their crews out of burning buildings moments before the structure collapses, even though they cannot immediately explain what triggered the warning. Later analysis often reveals subtle clues, changes in sound, heat or airflow, that the subconscious mind detected before the conscious mind had time to interpret them. The same hidden processes shape many of the experiences we consider ordinary. A familiar smell can suddenly trigger memories from childhood that you had not thought about in years. An emotional reaction can appear before you have time to analyze what you are feeling. Entire routines, from driving a car to typing on a keyboard, can unfold automatically while your conscious thoughts are focused somewhere else entirely. Beneath the narrow stream of awareness we experience each moment lies a vast network of systems storing memories, evaluating risks, recognizing patterns, and preparing actions long before we realize what is happening. Even when the conscious mind finally goes quiet at night, those systems continue working. During sleep, the brain sorts through memories, processes emotions, and sometimes produces dreams so vivid they feel indistinguishable from reality. These dreams often combine fragments of past experiences with imagined scenarios, revealing how active the subconscious mind remains, even when awareness fades. As scientists have studied the brain more closely, a remarkable picture has begun to emerge. The conscious mind, which feels so central to our identity, may represent only a small part of a much larger system operating behind the scenes. Beneath the surface of awareness lies an intricate network, constantly interpreting the world, predicting the future, shaping emotions, and guiding behavior long before conscious thought enters the process. And that realization leads to a strange and fascinating question. If the subconscious mind is already processing enormous amounts of information, anticipating events, and even initiating decisions before we become aware of them, then what exactly is the role of the conscious mind itself? Understanding that hidden system is one of the greatest challenges in modern science, and exploring it reveals a story far more mysterious than most of us ever imagine. Tonight, we're going to explore that story and uncover the hidden system quietly running your life. The subconscious mind. Chapter 1. The mind you don't control. For most of human history, people believed the conscious mind was the command center of behavior. When we decide to stand up, speak, or reach for an object, it feels as though a deliberate choice has just been made. Thoughts appear in our awareness. We weigh possibilities, and then we act. This sense of control feels so natural that it rarely comes into question. After all, every moment of experience seems to confirm the same simple idea. We are aware of our thoughts, and those thoughts guide what we do. But over the past century, psychology and neuroscience have uncovered a far more complicated reality. Beneath the narrow stream of thoughts we experience each moment lies a vast system of unconscious processes constantly working behind the scenes. These hidden systems interpret sensory information, regulate emotions, coordinate movement, retrieve memories, predict the future, and prepare actions long before we become aware of any decision taking place. In many ways, the conscious mind may not be directing events at all. It may simply be observing the final result of processes that began long before awareness arrived. One of the most striking ways to understand this imbalance comes from research into how much information the brain actually processes. Every second, the human nervous system receives an enormous flood of signals from the outside world. Photons strike the retina, producing complex visual patterns. Vibrations reach the inner ear as sound. Pressure receptors in the skin detect temperature and movement. Chemical molecules trigger smell and taste receptors. Meanwhile, signals from muscles, organs, and the inner ear constantly update the brain about body position, balance, hunger, heart rate, and breathing. When scientists attempt to estimate the total amount of information entering the brain each second, the numbers are staggering. Some cognitive researchers estimate that the nervous system processes roughly 11 million bits of sensory information every second. Yet the conscious mind appears capable of focusing on only a tiny fraction of that data, perhaps 40 bits per second at most. This means that the overwhelming majority of information our brain handles never reaches conscious awareness at all. Instead, the brain relies on an elaborate filtering system. Subconscious neural networks analyze incoming information automatically, identifying patterns, predicting outcomes, and determining which details are important enough to pass along to consciousness. Everything else is handled silently in the background. The conscious mind receives only a simplified summary of what the brain has already processed. Consider how effortless something like walking through a crowded street feels. Your eyes scan the environment, identifying moving people, approaching vehicles, changing traffic lights, and uneven pavement. Your brain estimates distances, predicts the movement of strangers, calculates safe walking paths, and coordinates hundreds of muscles to keep your body balanced. At the same time, you might be thinking about an upcoming meeting, listening to music, and planning what to eat for dinner. The remarkable thing is that most of the complex calculations required to navigate the environment never enter awareness. The brain performs them automatically. Consciousness experiences only the final result, the feeling of smoothly moving through space. One of the clearest demonstrations of subconscious control appears in a phenomenon psychologists sometimes call highway hypnosis. Many drivers have experienced the strange sensation of arriving at a destination with little memory of the journey itself. During the drive, the brain correctly responded to traffic signals, adjusted speed, navigated turns, and avoided obstacles. Yet conscious attention was focused elsewhere, perhaps on a conversation, a daydream, or a distant thought. Despite this lapse in awareness, the brain's motor systems continued operating flawlessly. Learned driving patterns, stored through repetition and practice, were executed automatically by deeper neural circuits. Only when something unusual occurs, a sudden brake light, a horn, or an unexpected obstacle, does conscious attention suddenly snap back into focus. Habits reveal a similar pattern. Many of the routines that fill everyday life unfold with almost no conscious planning. Brushing teeth, tying shoes, typing on a keyboard, opening familiar doors, and walking through a workplace often occur with remarkable efficiency, even when the mind is distracted. These behaviors are largely controlled by a network of structures deep within the brain known as the basal ganglia. The basal ganglia specialize in learning repeated sequences of behavior. When a new task is first attempted, the conscious mind must guide each step carefully. Over time, however, repeated practice allows the brain to convert these actions into automatic routines. Once this transition occurs, control shifts away from conscious planning and into subconscious circuits designed to run the behavior with minimal effort. This process allows the brain to conserve energy. Conscious thought is relatively slow and metabolically expensive. Automatic processing, by contrast, allows the brain to handle complex behaviors rapidly while freeing conscious awareness to focus on novel problems. Emotional reactions provide another powerful glimpse into the speed of subconscious systems. Imagine walking through a quiet building late at night when suddenly a loud crash echoes from another room. Before you have time to interpret what happened, your body may already react. Your muscles tense, your heart rate jumps, your head turns toward the sound. These reactions can occur within fractions of a second. Neuroscientists have discovered that certain sensory signals travel along extremely fast neural pathways connecting the thalamus and the amygdala, a region deeply involved in threat detection. These circuits allow the brain to trigger defensive reactions before the conscious mind has even finished interpreting what the stimulus was. From an evolutionary perspective, this rapid response system was essential for survival. Early humans who paused to carefully analyze every rustle in the grass might not survive long enough to determine whether the sound came from wind or from a predator. By allowing the subconscious brain to initiate defensive reactions instantly, the nervous system increased the chances of survival. Yet the speed of these responses also reveals something unsettling. The body often reacts before the mind understands why. Psychologists studying human judgment have uncovered similar patterns in decision-making. In many experiments, people make surprisingly rapid choices based on subtle cues they cannot consciously identify. Facial expressions, tone of voice, body language, and environmental context all influence perception in ways that rarely reach awareness. After making a decision, the conscious mind often constructs a narrative explaining why the choice seemed reasonable. But in many cases, the explanation may be a reconstruction rather than the true cause. The decision itself may have emerged from subconscious pattern recognition long before conscious reasoning entered the process. This phenomenon has been observed repeatedly in studies of intuition. Experts in certain fields, such as firefighters, physicians, and chess masters, can sometimes make remarkably accurate decisions within seconds. Experienced firefighters have reported sensing that a building was about to collapse moments before visible warning signs appeared. Chess grandmasters can glance at a board and immediately recognize strong or weak positions, without calculating every possible move. In these cases, the brain draws upon thousands of stored experiences to detect patterns almost instantly. The subconscious mind performs a rapid comparison between the current situation and countless past scenarios, producing an intuitive sense of what might happen next. Conscious reasoning may later analyze the decision, but the initial judgment often emerges from processes that occur entirely outside awareness. All of this evidence suggests that the conscious mind occupies only a small role in the vast network of processes shaping behavior. Beneath the surface of awareness, the brain constantly interprets information, predicts outcomes, initiates actions, and generates emotional responses long before thoughts appear in the spotlight of consciousness. The experience of being in control may therefore arise from something quite different than we assume. Rather than directing every action, consciousness may function more like a narrator observing events already set in motion by deeper brain systems. Thoughts may feel like commands, but they might actually be explanations appearing after the brain has already begun to act. This idea challenges one of the most fundamental assumptions about human identity. If the subconscious mind is responsible for most perception, emotion, and decision-making, then the conscious self we experience may represent only the final stage of a much larger process. The feeling of deliberate control might be less like steering a vehicle and more like sitting in the passenger seat while the journey unfolds. Throughout the 20th century, scientists began searching for ways to test this unsettling possibility. With the development of new technologies capable of measuring electrical activity in the brain, researchers could finally observe neural processes as they happened in real time. If subconscious systems truly initiated decisions before conscious awareness appeared, then it might be possible to detect the earliest signals of those decisions forming inside the brain. What they eventually discovered would challenge one of the most deeply rooted beliefs about human nature. Scientists eventually found evidence suggesting that the brain sometimes begins making decisions before we even realize we have chosen anything at all. And the experiments that revealed this possibility would become some of the most controversial studies in the history of neuroscience. Chapter 2: The Experiments That Predicted Your Decisions. In the early 1980s, neuroscience was entering a period of rapid technological progress. Researchers had already learned that electrical signals produced by neurons could be detected from outside the skull using a technique called electroencephalography, or EEG. This method allowed scientists to observe patterns of brain activity unfolding in real time with millisecond precision. For the first time, it became possible to track the neural signals that appeared just before a person performed an action. One scientist who became deeply interested in these signals was Benjamin Libet, a physiologist working at the University of California, San Francisco. Libet had spent much of his career studying the relationship between brain activity and conscious experience. Like many researchers of his time, he was fascinated by one of the oldest philosophical questions in human history. When does a decision actually occur? From our own perspective, the answer seems obvious. We experience ourselves deciding to act, and then we act. The thought appears first, followed by the movement. But Libet suspected that the sequence might not be quite so simple. He wondered whether the brain might begin preparing actions before the conscious mind even realized a decision had been made. To test this idea, Libet designed a deceptively simple experiment that would later become one of the most famous studies in neuroscience. Volunteers were seated comfortably in a laboratory chair and asked to watch a specially designed clock-like display. Instead of a traditional clock hand, a bright dot rotated rapidly around the circle, completing a full revolution every few seconds. The display allowed participants to identify precise moments in time. The task itself was straightforward. Participants were instructed to flex their wrist whenever they felt the spontaneous urge to do so. They were not told when to move, and they were asked not to plan the movement in advance, Instead, they were supposed to act whenever the impulse appeared naturally in their mind. While participants performed this task, electrodes placed on the scalp recorded electrical signals produced by their brains. These signals allowed Libet and his colleagues to observe neural activity occurring in regions involved in movement. At the same time, sensors attached to the wrist detected the exact moment when the muscle actually flexed. The final piece of the experiment involved conscious awareness. After each movement, participants were asked to report the exact position of the rotating dot at the moment they first became aware of their intention to move. In other words, they had to identify when the feeling of, "I am about to move my wrist," entered their consciousness. By comparing these three events, the brain activity, the reported moment of intention, and the physical movement, Libet hoped to determine the sequence in which decisions unfolded inside the brain. What the researchers discovered was both surprising and deeply unsettling. The EEG recordings revealed a slow buildup of electrical activity in the brain's motor regions beginning roughly 500 milliseconds before the wrist movement occurred. This signal had actually been discovered earlier by German neuroscientists Hans Helmut Kornhuber and Luder Dicke in the 1960s, who called it the readiness potential or Bereitschaftspotential. The signal appeared to represent the brain preparing to initiate a voluntary movement. Libet's experiment added a crucial new element: the timing of conscious awareness. Participants typically reported becoming aware of their intention to move only about 200 milliseconds before the movement itself. This meant that the readiness potential, the brain's preparation for action, began roughly 300 milliseconds before the person consciously decided to act. In simple terms, the brain appeared to start preparing the movement before the conscious mind became aware of deciding to perform it. For many scientists and philosophers, this result was startling. The traditional view of human decision-making assumed that conscious thought initiated voluntary actions. But Libet's findings suggested something quite different. The earliest neural signals involved in the decision appeared to occur before conscious awareness entered the process. Libet himself was careful not to overstate the implications of his work. Although the readiness potential appeared before conscious intention, he proposed that the conscious mind might still play an important role during the final moments before the action occurred. According to his interpretation, consciousness might not initiate decisions, but it might still have the ability to stop them. Libet called this possibility the veto hypothesis. In this model, subconscious brain processes generate potential actions automatically. These impulses rise toward execution as the readiness potential builds. However, during the final fraction of a second before the movement occurs, the conscious mind may still have the ability to cancel the action. Libet sometimes referred to this idea informally as free won't rather than free will. Instead of actively choosing actions, consciousness might function as a supervisory system capable of preventing certain behaviors from occurring. Even with this interpretation, the experiment raised a troubling question. If subconscious neural activity initiates decisions before conscious awareness appears, then the experience of making a choice might actually be arriving after the brain has already begun acting. In the decades that followed, Libet's experiment became one of the most widely discussed studies in neuroscience. Some researchers viewed it as evidence that free will might be an illusion. Others argued that the experimental design involved extremely simple actions that might not reflect real-world decision-making. The debate remained unresolved for many years. Then, in the early 21st century, advances in brain imaging technology allowed scientists to revisit the question with far more powerful tools. One of the most influential follow-up studies occurred in 2008, when a team led by neuroscientist John Dylan Haynes at the Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig conducted a new series of experiments using functional magnetic resonance imaging, or fMRI. Unlike EEG, which measures electrical activity with excellent timing but limited spatial precision, fMRI allows scientists to observe activity across different regions of the brain by detecting changes in blood flow associated with neural activity. This technique makes it possible to identify which brain structures are involved in specific mental processes. Haynes and his colleagues designed an experiment similar in spirit to Libet's original study. Participants lay inside an fMRI scanner while watching a screen displaying letters appearing in sequence. At any moment they chose, they were instructed to press either a left button or a right button. After pressing the button, they reported which letter was on the screen when they first became aware of their decision. This setup allowed the researchers to determine the moment of conscious awareness in a manner similar to Libet's rotating clock. The crucial difference involved the analysis of brain activity before the decision occurred. Instead of looking for a single signal like the readiness potential, the researchers used machine learning algorithms to analyze patterns of activity across multiple brain regions. These algorithms attempted to determine whether certain neural patterns could predict which button a participant would eventually press. The results revealed something remarkable. Patterns of brain activity in regions such as the frontopolar cortex and parietal cortex contained information about the participant's eventual decision several seconds before the person reported becoming aware of choosing. In some cases, the algorithms could predict which button a participant would press up to 7 seconds before the conscious decision was reported. Although the predictions were not perfect, accuracy hovered around 60%, they were significantly above chance. This suggested that the brain had already begun forming the decision long before it entered conscious awareness. For many observers, the 7-second gap was particularly striking. Libet's experiment had shown a delay of a few hundred milliseconds between unconscious preparation and conscious intention. The fMRI studies appeared to extend that timeline dramatically. If the brain could begin shaping decisions several seconds before awareness appeared, then the conscious mind might be entering the process far later than previously imagined. Following the publication of Haynes's study, other researchers began exploring similar questions using a variety of experimental designs. Laboratories across Europe, North America, and Asia conducted experiments examining the neural signals associated with voluntary decisions. Many of these studies identified early brain activity in areas such as the supplementary motor area, prefrontal cortex, and parietal regions before participants reported conscious intentions. In some cases, neural signals predicting upcoming actions appeared seconds before individuals believed they had made a choice. These findings generated enormous discussion within neuroscience and philosophy. Some researchers argued that the experiments demonstrated a fundamental limitation of conscious control. According to this interpretation, decisions might originate in subconscious neural processes, while consciousness merely becomes aware of the outcome later. Others offered more cautious interpretations. Critics pointed out that the tasks used in these experiments involved extremely simple actions, pressing buttons or flexing wrists without meaningful consequences. Real-world decisions, such as choosing a career, forming relationships, or making moral judgments, involve complex reasoning, emotional evaluation, and long-term planning. It is possible that these more complicated decisions engage consciousness more deeply than the simplified laboratory tasks used in the studies. Another important criticism involves the predictive accuracy of the results. Even in the most sophisticated experiments, the algorithms predicting decisions rarely exceeded 60% accuracy. This means that although early brain activity contains information about upcoming actions, it does not determine them with certainty. In other words, the brain may be leaning toward a particular decision early on, but the final outcome could still change before the action occurs. Despite these debates, one conclusion has gained widespread acceptance among neuroscientists. The process of decision-making does not begin at the moment we become aware of choosing. Instead, a complex cascade of neural activity unfolds beneath the surface of consciousness before awareness enters the scene. The conscious mind appears to be joining the process after it has already begun. This realization has profound implications for how we understand human behavior. The experience of choosing may feel immediate and deliberate, but the brain's internal machinery may have been working on the decision long before we noticed. Rather than acting as the brain's central command center, consciousness might function more like a late-arriving observer, one that interprets decisions already taking shape within deeper neural systems. To understand how this hidden machinery operates, scientists began examining the internal architecture of the brain itself. Beneath the surface of awareness lies an intricate network of structures responsible for emotion, habit formation, threat detection, prediction, and automatic movement. These systems process enormous amounts of information simultaneously, coordinating behavior with remarkable efficiency while remaining almost entirely invisible to conscious experience. In the next chapter, we explore the hidden systems inside the brain, uncovering the neural networks that quietly guide perception, emotion, and behavior long before our conscious mind realizes what is happening. Chapter 3. The hidden systems inside your brain. The human brain is often described as the most complex structure known to exist, containing an estimated 86 billion neurons connected through hundreds of trillions of synapses. It forms an intricate network capable of processing extraordinary amounts of information at once. Each neuron communicates through electrochemical signals that travel across vast interconnected pathways, creating patterns of activity that allow the brain to interpret the world, guide behavior, regulate emotions, and maintain the internal stability required for survival. Yet, despite this immense complexity, the conscious mind experiences only a narrow stream of thoughts, sensations, and intentions at any given moment. Beneath that thin layer of awareness lies a much larger system of neural processes that operate quietly in the background. Understanding the subconscious mind requires looking beyond the thoughts we experience directly and exploring the specialized structures responsible for perception, emotion, memory, and automatic behavior. Over the past several decades, advances in brain imaging and neurophysiology have revealed that many of the brain's most important functions occur outside conscious awareness. While the conscious mind feels like the center of decision-making, deeper neural systems are constantly analyzing information, predicting outcomes, and preparing actions before those processes ever reach awareness. One of the most important groups of structures involved in subconscious processing lies deep within the brain and is collectively known as the limbic system. Although scientists continue to debate the exact boundaries of this system, it generally includes regions such as the amygdala, hippocampus, hypothalamus, and parts of the cingulate cortex. These structures play central roles in emotional processing, memory formation, and motivation. Rather than operating through deliberate reasoning, the limbic system responds rapidly to sensory information, often generating emotional reactions before the conscious mind has had time to interpret what is happening. Among these structures, the amygdala has become one of the most extensively studied components of the emotional brain. Roughly almond-shaped and located deep within the temporal lobes, the amygdala functions as a rapid threat detection system. During the late 20th century, neuroscientist Joseph Ledoux conducted influential experiments demonstrating that sensory information can reach the amygdala through extremely fast neural pathways that bypass slower cortical processing. This shortcut allows the brain to respond to potential threats almost instantly. In practical terms, this means the brain can trigger defensive reactions before the conscious mind understands what is happening. If a sudden movement appears in the corner of your eye, your body may jump or turn toward the stimulus immediately. Only afterward does the conscious mind analyze the situation and determine whether the movement represented a real danger or something harmless. This rapid pathway provided a crucial evolutionary advantage for early humans and other animals, allowing them to react quickly to predators or other threats in their environment. The limbic system is also closely connected to the hippocampus, a structure essential for forming and organizing memories. Located adjacent to the amygdala, the hippocampus helps convert short-term experiences into long-term memories. It also plays a role in spatial navigation and contextual learning, allowing the brain to link events with specific environments. While the hippocampus can contribute to memories that eventually reach conscious awareness, much of its processing occurs automatically as experiences unfold. Emotion and memory are deeply intertwined within this system. When emotionally significant events occur, the amygdala interacts with the hippocampus to strengthen memory formation. This is why highly emotional experiences, such as accidents, celebrations, or moments of fear, are often remembered with vivid detail. The brain prioritizes these memories because they may contain information important for future survival. Another major component of subconscious behavior lies within a group of structures known as the basal ganglia. Located near the center of the brain, the basal ganglia are deeply involved in habit formation, motor control, and procedural learning. These structures help transform repeated actions into automatic routines that can be executed with little conscious effort. When a person first learns a new skill, the prefrontal cortex, which is responsible for planning and deliberate reasoning, becomes heavily involved in guiding each step of the process. Over time, however, repeated practice gradually shifts control of the behavior toward the basal ganglia. Brain imaging studies have shown that as skills become habitual, activity in the prefrontal cortex decreases, while activity in the basal ganglia increases. This shift allows complex behaviors to become automatic. A beginner learning to play the piano must consciously think about every movement of the fingers. A skilled pianist, by contrast, can perform intricate sequences of notes while simultaneously focusing on expression or musical interpretation. The brain has effectively transferred control of the mechanical aspects of the task into subconscious circuits. Habits, both beneficial and harmful, rely heavily on these systems. Everyday routines such as tying shoelaces, typing on a keyboard, or driving along a familiar route are governed largely by the basal ganglia. Once established, these patterns can be triggered automatically by environmental cues, sometimes operating so smoothly that the conscious mind barely notices them unfolding. Movement itself depends on another specialized structure that operates almost entirely outside awareness: the cerebellum. Located at the back of the brain beneath the occipital lobes, the cerebellum contains more neurons than the rest of the brain combined, despite occupying only a small portion of its total volume. This dense neural structure plays a crucial role in coordinating movement, maintaining balance, and refining motor actions. Whenever a person reaches for an object, walks across a room, or adjusts their posture, the cerebellum continuously compares intended movements with sensory feedback from muscles and joints. It makes rapid corrections to ensure that actions remain smooth and precise. These adjustments occur so quickly that they rarely enter conscious awareness. Without the cerebellum's constant fine-tuning, even simple movements would become clumsy and inaccurate. Patients with cerebellar damage often experience severe coordination problems, demonstrating just how much of our everyday motor control depends on subconscious neural systems. Beyond these individual structures, modern neuroscience has revealed that the brain also operates through large-scale networks of interconnected regions that coordinate activity across different areas. One of the most intriguing of these networks is known as the default mode network, or DMN. The discovery of the default mode network occurred somewhat unexpectedly in the early 2000s, as researchers began using functional magnetic resonance imaging to observe brain activity during different mental states. Scientists noticed that certain brain regions consistently became more active when participants were resting quietly rather than performing specific tasks. Instead of shutting down during periods of inactivity, these regions appeared to form a coordinated network that remained highly active when the mind was wandering. Key components of the default mode network include the medial prefrontal cortex, posterior cingulate cortex, precuneus, and parts of the parietal lobes. This network appears to play an important role in processes such as self-reflection, memory integration, and imagining possible future scenarios. When people drift into daydreams, reflect on past experiences, or imagine future possibilities, activity within the default mode network increases. These processes often occur spontaneously, without deliberate intention, suggesting that the brain is constantly constructing narratives and simulations, even when the conscious mind is not actively focused on a task. Some researchers believe the default mode network may contribute to the brain's ongoing construction of a personal identity. By integrating memories, emotions, and imagined possibilities, the network helps create the continuous story we experience as our sense of self. Even when we are resting quietly, the brain may be actively maintaining this narrative framework beneath conscious awareness. In addition to these networks, many neuroscientists now view the brain as a predictive system, constantly attempting to anticipate what will happen next. According to the theory of predictive processing, the brain does not simply react to incoming sensory information. Instead, it continuously generates predictions about the world and compares them with the signals arriving from the senses. When sensory input matches the brain's expectations, perception feels smooth and stable. When the input deviates from the prediction, the brain updates its internal models to better reflect reality. This predictive process occurs at multiple levels throughout the brain, from basic sensory interpretation to complex social understanding. For example, when listening to someone speak, the brain often predicts upcoming words based on context and past experience. When catching a ball, the brain estimates the ball's trajectory before it reaches the hand. These predictions allow the nervous system to respond quickly and efficiently, reducing the need for slow, deliberate analysis. The predictive nature of the brain helps explain why perception sometimes feels effortless. Rather than constructing every moment of experience from raw sensory data, the brain relies heavily on its expectations about what is likely to occur. Conscious awareness receives the final interpretation produced by this predictive machinery. The more scientists examine these hidden systems, the clearer it becomes that consciousness represents only a small window into the brain's overall operations. Beneath that window lies an immense network of specialized structures coordinating perception, emotion, memory, and action simultaneously. Much of this activity occurs automatically, without requiring deliberate thought or conscious awareness. In many situations, these systems are capable of processing information entirely outside conscious perception. The brain may detect patterns, recognize objects, and guide behavior even when the conscious mind believes it has no access to that information. One of the most remarkable demonstrations of this separation between perception and awareness comes from a neurological condition known as blind sight. In certain individuals who have suffered damage to the visual cortex, the conscious experience of sight disappears completely. These patients report that they are unable to see anything in portions of their visual field. Yet astonishingly, their brains can still respond to visual information. Experiments have shown that some of these patients can identify the location of objects, detect movement, and even navigate around obstacles despite insisting that they cannot see at all. Their brains appear to be processing visual signals without generating the conscious experience of vision. This phenomenon reveals just how powerful subconscious neural systems can be. The brain may continue interpreting the world even when conscious awareness fails to register the information. The next chapter explores this extraordinary discovery in detail. revealing how the brain can sometimes see without the mind ever realizing it. Chapter 4. The Brain That Sees Without You. In the early 1970s, neurologists studying patients with brain injuries encountered a phenomenon so unusual that it initially seemed almost impossible. Some patients who had suffered damage to regions of the brain responsible for vision insisted that they were completely blind in certain areas of their visual field. When asked directly whether they could see anything in those regions of space, they would confidently respond that they saw nothing at all. Yet when researchers designed experiments that forced these individuals to make guesses about visual information appearing in their blind areas, something remarkable happened. The patients often answered correctly far more frequently than random chance would allow. This puzzling condition eventually became known as blind sight, and it remains one of the most striking demonstrations that perception and conscious awareness are not the same thing. Blind sight reveals that the brain can continue to analyze visual information even when the conscious experience of seeing has disappeared. In other words, the brain may still be interpreting the world while the mind believes it is blind. To understand how this phenomenon occurs, it helps to examine the normal pathway that visual information follows through the brain. Light enters the eye through the pupil and is focused onto the retina at the back of the eye. Specialized cells in the retina convert this light into electrical signals, which travel along the optic nerve toward the brain. These signals are first relayed through a structure deep within the brain called the lateral geniculate nucleus, part of the thalamus, before being transmitted to the primary visual cortex in the occipital lobe at the back of the head. The primary visual cortex, often referred to as V1, plays a critical role in transforming raw visual signals into the patterns of perception that form our conscious visual experience. Within this region, neurons respond to specific visual features such as edges, orientation, contrast, and motion. As information moves through higher visual areas beyond V1, the brain gradually constructs a detailed representation of objects, faces, movement, and spatial relationships. This complex process ultimately produces the vivid experience we describe as seeing. When the primary visual cortex is damaged, often by stroke, traumatic injury, or surgical removal of tumors, patients typically lose conscious vision in the corresponding region of space. This condition is sometimes called cortical blindness. From the perspective of the patient, the affected part of the visual field appears completely dark and empty. No shapes, colors, or motion are visible there. In the early days of neurological research, it was assumed that once this region of the brain was destroyed, visual perception in that part of the field was entirely impossible. However, careful experimentation began to reveal that the story was not quite so simple. One of the first scientists to investigate this mystery in depth was Lawrence Weisskranz, a British psychologist working at the University of Oxford. During the 1970s, Weisskranz began studying a patient known in scientific literature simply as DB. DB had undergone surgery to remove a tumor that damaged a portion of his primary visual cortex, leaving him with a blind region on one side of his visual field. When DB was asked whether he could see objects in that area, he consistently reported that he could not. From his perspective, that region of space appeared entirely blank. But Weisskranz wondered whether some level of visual processing might still be occurring outside conscious awareness. To test this possibility, researchers designed experiments in which visual stimuli, such as flashes of light or simple shapes, were presented within DB's blind field. Instead of asking whether he could see the stimuli, the researchers asked him to guess where the stimulus appeared. The results were astonishing. Although DB insisted he could not see anything in the blind region, his guesses were frequently correct. When asked to point toward a light presented in the blind field, he could often identify its location accurately. When shown lines oriented either vertically or horizontally, he could guess their orientation correctly at rates far above chance. In some experiments, his accuracy exceeded 90%. Each time he made these correct responses, DB expressed surprise. He maintained that he had not actually seen the stimulus and was merely guessing. From the perspective of his conscious experience, this claim was entirely truthful. Yet the experimental data clearly showed that his brain was somehow processing visual information without producing the conscious experience of vision. Weisskranz coined the term blind sight to describe this strange condition, vision without sight. As more patients with similar injuries were studied, researchers began to realize that blind sight was not an isolated curiosity, but rather a window into the deeper architecture of the visual system. The brain does not rely on a single pathway for processing visual information. Instead, multiple parallel circuits analyze visual signals simultaneously, each contributing different aspects of perception and behavior. The primary pathway responsible for conscious vision involves the route from the retina to the thalamus and then to the primary visual cortex. This pathway is sometimes called the geniculostriate pathway, and it forms the backbone of conscious visual experience. When this pathway is disrupted, the vivid awareness of sight disappears. However, scientists discovered that additional pathways exist that allow visual information to reach other parts of the brain without passing through the primary visual cortex. One of these routes involves connections between the retina and a structure in the midbrain known as the superior colliculus. This structure plays an important role in directing eye movements and orienting attention toward objects in the environment. Signals processed through the superior colliculus can influence behavior even when the visual cortex is damaged. These circuits evolved very early in vertebrate history and are shared by many animals, including reptiles and birds. Their primary purpose appears to be guiding rapid reactions to visual stimuli rather than producing detailed conscious perception. Because these pathways bypass the regions responsible for conscious vision, they can continue operating even when a person reports that they cannot see. Over time, researchers discovered that blind sight patients could demonstrate a surprising range of abilities. Some could detect the direction of moving objects within their blind field. Others could point toward objects or avoid obstacles while walking through a room. In certain experiments, patients were able to reach for objects located in their blind field with remarkable accuracy, despite insisting that they had no visual awareness of them. Perhaps even more intriguing were studies exploring whether emotional information could be processed without conscious sight. During the late 1990s and early 2000s, neuroscientists conducted experiments presenting images of faces displaying different emotional expressions, such as fear or happiness, within the blind fields of blind sight patients. Although the participants insisted that they could not see the faces, brain imaging revealed that emotional processing centers, such as the amygdala, responded differently depending on the facial expression presented. In some cases, patients could even guess whether a face was fearful or happy at rates higher than chance. These findings suggest that certain aspects of emotional perception may occur through subconscious pathways linking visual regions to the limbic system. The brain appears capable of detecting emotionally significant signals even when conscious awareness of the stimulus is absent. Blind sight, therefore, challenges one of our most basic assumptions about perception. Most people intuitively believe that seeing is equivalent to being aware of visual information. Yet the evidence from blind sight demonstrates that visual processing and visual awareness can exist independently. The brain may continue interpreting shapes, motion, and emotional cues even when the conscious mind experiences nothing at all. This realization has profound implications for our understanding of consciousness. It suggests that awareness is not required for the brain to analyze sensory information or guide behavior. Instead, conscious perception may represent only one layer within a much larger hierarchy of neural processing. In everyday life, these subconscious visual systems likely operate continuously alongside conscious perception. Even when our vision appears normal, the brain may be detecting subtle environmental signals that never reach awareness. Small changes in body language, fleeting movements in peripheral vision, or faint emotional expressions on faces may influence our reactions long before we consciously notice them. Psychologists studying social perception have found evidence supporting this idea. People often respond to facial expressions, gaze direction, and posture automatically, adjusting their behavior within fractions of a second. These reactions frequently occur before individuals consciously recognize what they have seen. The brain's visual system, therefore, appears to function as a layered architecture. One level produces the vivid experience of sight that enters conscious awareness. Beneath that level lies a network of faster, more automatic systems designed to guide behavior rapidly and efficiently. Most of the time, these systems operate together seamlessly, giving the impression that perception and awareness are inseparable. Blind sight reveals what happens when those systems become separated. By studying patients whose conscious vision has been disrupted, neuroscientists gain a rare glimpse into the hidden mechanisms that normally operate beneath awareness. These cases show that the brain can continue perceiving and responding to the environment, even when conscious experience fails to register the information. The phenomenon, therefore, raises an unsettling possibility. If the brain can analyze visual information without awareness, in extreme cases like blind sight, how often might similar subconscious processing occur in everyday perception? Even when we believe we are fully aware of what we see, vast amounts of visual information may still be processed outside the spotlight of consciousness. The brain's hidden systems may be evaluating patterns, detecting threats, and guiding behavior long before those signals reach the mind. And vision is only one example. Increasingly, neuroscientists have begun to realize that the brain does not simply react to the world around it. Instead, it constantly attempts to predict what will happen next. Beneath conscious awareness, neural systems continuously construct internal models of the environment, forecasting events and preparing actions before they occur. This predictive ability allows the brain to respond with extraordinary speed and efficiency, shaping perception and behavior in ways that often feel almost intuitive. In the next chapter, we explore this remarkable predictive machinery, revealing how the subconscious mind constantly anticipates the future in order to guide every moment of human experience. Chapter 5: The Brain's Prediction Machine. For much of the 20th century, scientists believed that perception operated in a relatively straightforward manner. According to the traditional view, the brain functioned primarily as a passive receiver of information from the external world. Light entered the eyes, sound waves reached the ears, and signals from the body traveled through sensory nerves to the brain. The brain then interpreted these signals and constructed the experience we call reality. In this model, perception was largely a bottom-up process in which sensory input flowed inward and was gradually assembled into conscious experience. Over the past several decades, however, a growing body of research has challenged this assumption. Increasingly, neuroscientists and cognitive scientists have begun to view the brain not simply as a receiver of information, but as an active prediction system. Rather than waiting for sensory data to arrive and then interpreting it, the brain appears to be constantly anticipating what will happen next. It generates expectations about the world based on past experience and uses incoming sensory information primarily to confirm or adjust those expectations. This perspective is known as predictive processing, and it has become one of the most influential theoretical frameworks in modern neuroscience. According to this view, the brain continuously builds internal models of the environment. These models allow it to forecast what sights, sounds, and sensations are likely to occur in the immediate future. Incoming sensory signals are then compared against these predictions. When the signals match the prediction, the brain's model remains stable. When the signals differ from what was expected, the discrepancy, called a prediction error, is used to update the brain's internal model so that future predictions become more accurate. In effect, the brain is constantly running a simulation of reality, testing its expectations against incoming sensory information and refining those expectations over time. This predictive process helps explain why familiar environments feel so easy to navigate. When you walk through your own home in the dark, you can often move around with surprising confidence, even without clearly seeing the furniture. Your brain already knows where objects are likely to be located based on past experience. The brain predicts the layout of the room and prepares motor commands accordingly. As long as the predictions match the environment, movement feels effortless and automatic. However, if something unexpected has changed, perhaps a chair has been moved into the walkway, your foot may suddenly collide with the obstacle. At that moment, the brain experiences a prediction error. The unexpected sensory feedback forces the brain to revise its internal model, and conscious attention quickly becomes engaged as you adjust your movement. Predictive processing, therefore, allows the brain to conserve enormous amounts of energy. Instead of analyzing every detail of sensory input from scratch, the brain relies on its expectations to fill in much of the information automatically. Conscious attention is recruited primarily when something violates those expectations. This principle may extend far beyond simple navigation. Some neuroscientists now argue that perception itself is largely shaped by prediction. The visual system, for example, does not merely record the external world like a camera. Instead, it continuously compares incoming signals with expectations generated by higher brain regions. What we consciously perceive may therefore represent the brain's best prediction about the causes of sensory input, rather than a direct representation of the world itself. Evidence for this idea can be seen in a variety of perceptual illusions. In some optical illusions, the brain's expectations lead it to interpret ambiguous images in ways that do not accurately reflect the physical stimulus. For example, when viewing certain shaded patterns, the brain automatically assumes that light is coming from above, because that is the most common lighting condition in the natural world. As a result, identical shapes can appear either convex or concave, depending on how the shading interacts with this expectation. These illusions demonstrate that perception depends not only on the information entering the eyes, but also on the brain's assumptions about what the world should look like. Predictive processing also provides insight into a phenomenon that many people describe as intuition. Intuition is often experienced as a sudden feeling that something is right or wrong without consciously knowing why. A person might instantly sense that a situation is dangerous, that a decision is correct, or that a pattern is meaningful even though they cannot articulate the reasoning behind the judgment. For many years, intuition was sometimes viewed as mysterious or even mystical. Today, psychologists increasingly understand it as the result of rapid subconscious pattern recognition. The brain draws upon a vast store of past experiences, comparing the current situation with thousands of similar situations encountered previously. When a match is detected, the brain generates an immediate response that feels like a sudden insight. One of the most famous examples of this process comes from research conducted by Gary Klein, a cognitive psychologist who studied decision-making among experienced professionals such as firefighters, military commanders, and emergency responders. During the 1980s, Klein and his colleagues interviewed firefighters who had made life-saving decisions during dangerous situations. In one widely cited case, a fire captain and his crew were battling what appeared to be a routine kitchen fire in a residential building. As they worked to extinguish the flames, the captain suddenly experienced an uneasy feeling that something was wrong. The fire seemed strangely quiet, and the heat in the room felt unusually intense. Without fully understanding why, he immediately ordered his team to evacuate the building. Moments after they left the room, the floor collapsed beneath them. The fire had actually been burning in the basement below the kitchen, weakening the structure from underneath. When the captain later tried to explain his decision, he initially struggled to identify the exact cues that had triggered his alarm. Only after careful reflection did he realize that subtle details, such as the unusual heat pattern and the absence of expected crackling sounds, had alerted his brain that the situation did not match familiar patterns. His subconscious predictive system detected the mismatch and generated an urgent warning before his conscious mind fully understood the danger. Similar processes appear in many fields where experts develop extensive experience. In medicine, experienced physicians often recognize patterns of symptoms almost instantly. A doctor who has seen thousands of patients may be able to identify certain illnesses within seconds of observing a patient's appearance, posture, or breathing pattern. Although careful diagnostic reasoning still plays an important role, the initial impression frequently emerges from subconscious pattern recognition. Research on chess expertise provides another striking example. Studies conducted by cognitive scientist Adrian de Groot and later expanded by researchers such as Herbert Simon revealed that chess grandmasters do not rely primarily on calculating every possible move. Instead, they recognize complex board configurations as familiar patterns built from thousands of previous games. This allows them to evaluate positions and identify strong moves within seconds. When a grandmaster glances at a chessboard, their brain rapidly compares the current arrangement of pieces with a vast library of stored patterns. The result is an intuitive sense of which strategies are promising and which are dangerous. Conscious analysis may follow, but the initial evaluation often occurs automatically. These examples illustrate the extraordinary power of the brain's predictive systems. By constantly comparing present conditions with stored experiences, the brain can anticipate likely outcomes and prepare responses with remarkable speed. At times, these rapid judgments can feel almost supernatural. People sometimes describe having a sudden sense that something is about to happen or that a situation is wrong, even when they cannot identify the reason. In reality, the brain may simply be detecting subtle cues that never reach conscious awareness. Despite its strengths, predictive processing is not perfect. Because the brain relies heavily on past experiences to form predictions, its expectations can sometimes lead to systematic errors in judgment. These errors are known as cognitive biases, and they represent situations in which the brain's predictions distort perception or reasoning. One well-known example is the availability heuristic, a bias in which people estimate the likelihood of events based on how easily examples come to mind. Dramatic events such as airplane crashes or shock attacks often receive extensive media coverage, making them easier to recall. As a result, people may overestimate how frequently these events occur, even though they are statistically rare. Another common bias is confirmation bias, the tendency to favor information that supports existing beliefs while ignoring evidence that contradicts them. Because the brain's predictive systems expect certain patterns, they may selectively interpret new information in ways that reinforce those expectations. These biases reveal the downside of a brain designed to predict rather than simply record reality. When predictions are accurate, perception feels smooth and efficient. When predictions are shaped by incomplete or misleading information, however, they can lead to mistaken conclusions. Even so, the predictive nature of the brain remains one of its most powerful capabilities. By anticipating what will happen next, the nervous system allows humans to respond quickly to changing environments, coordinate complex movements, and interpret ambiguous sensory signals. Some researchers now argue that nearly every aspect of perception involves prediction. The brain continuously forecasts the sensory consequences of actions, estimates the behavior of other people, and prepares responses before events unfold. Conscious awareness may therefore represent only the final stage of a much larger predictive process unfolding beneath the surface of the mind. Occasionally, however, this predictive machinery produces strange experiences that momentarily disrupt our sense of reality. One of the most intriguing examples is déjà vu, the eerie sensation that a present moment has somehow been experienced before. Although the exact cause of déjà vu remains uncertain, some neuroscientists believe it may arise when the brain's prediction systems briefly misfire, creating the false impression that an event had been anticipated in advance. In such moments, the boundary between prediction and memory becomes blurred, producing a powerful but fleeting sense of familiarity. Understanding the brain as a prediction machine reveals just how deeply our expectations shape our experience of the world. Beneath conscious awareness, the brain is constantly scanning the environment, comparing it with past experiences, and preparing responses long before we realize what is happening. But prediction and perception are not the only areas where the subconscious mind reveals its influence. There is another domain in which hidden thoughts, emotions, and memories emerge in vivid and sometimes bizarre forms. A mysterious landscape that appears every night when consciousness loosens its grip on waking reality. That landscape is the world of dreams. Chapter 6. Dreams from the Hidden Mind. Every night as the body begins to fall asleep, the brain undergoes a remarkable transformation. Conscious awareness gradually fades, muscles relax, breathing slows, and the electrical rhythms of neural activity shift into entirely different patterns. To an outside observer, sleep might appear to be a period of inactivity or rest. Yet inside the brain, an extraordinary sequence of processes is unfolding. In certain stages of sleep, neural activity becomes nearly as intense as it is during waking life. Within this altered neurological landscape, the subconscious mind often reveals itself through one of the most mysterious experiences humans have ever known: dreams. Dreaming is a universal human experience. Nearly every person dreams multiple times each night, even though many of those dreams are forgotten by morning. The vivid scenes, shifting narratives, and emotional experiences that unfold during dreams can feel as real as waking life while they are happening. Only after awakening does the mind recognize the strange logic of the dream world, where impossible events can unfold without raising suspicion. For thousands of years, dreams have fascinated human cultures across the globe. Ancient civilizations often treated dreams as messages from supernatural forces or glimpses of hidden truths. In ancient Mesopotamia, dream interpreters advised kings and rulers, believing that dreams carried prophetic meaning. The ancient Egyptians recorded dream interpretations on papyrus scrolls, associating certain dream images with specific future events. In classical Greece, temples known as asclepions functioned as dream sanctuaries where people would sleep in hopes of receiving healing visions from the gods. Even philosophers such as Aristotle speculated about the nature of dreams, suggesting that they might arise from internal sensations rather than divine intervention. Despite these early attempts to explain dreaming, the true biological basis of dreams remained mysterious for centuries. Scientific progress in understanding dreams accelerated dramatically in the 20th century with the development of technologies capable of measuring brain activity during sleep. One of the most important breakthroughs occurred in 1953 when a graduate student named Eugene Aserinsky, working under physiologist Nathaniel Kleitman at the University of Chicago, made an unexpected discovery while monitoring sleeping participants. Aserinsky noticed that during certain periods of sleep, the eyes of the participants moved rapidly beneath their closed eyelids. At the same time, recordings of their brain activity showed patterns that closely resembled the electrical signals observed during waking consciousness. This stage of sleep became known as rapid eye movement sleep, or REM sleep. When participants were awakened during REM sleep, They almost always reported vivid dreams. By contrast, when they were awakened during other stages of sleep, they were far less likely to recall dream experiences. This discovery provided the first strong scientific evidence linking a specific stage of sleep with dreaming. Further research revealed that a REM sleep occurs in repeating cycles throughout the night. After a person falls asleep, the brain typically enters REM sleep for the first time about 90 minutes later. This stage then reappears roughly every 90 minutes, with each REM period becoming longer as the night progresses. By the final hours of sleep, REM episodes can last 20 to 30 minutes at a time. During REM sleep, the brain exhibits a unique pattern of activity. Regions associated with visual imagery, emotion, and memory become highly active, while areas involved in logical reasoning and critical thinking show reduced activity. The prefrontal cortex, which plays a key role in decision-making and rational thought, becomes less active during REM sleep. This imbalance may help explain why dreams often contain unusual narratives that seem perfectly believable while they are happening. In the dream state, emotional and visual brain regions are highly active, creating vivid imagery and intense feelings. At the same time, the parts of the brain responsible for evaluating logic are relatively quiet, allowing improbable or impossible scenarios to unfold without triggering skepticism. While the discovery of REM sleep clarified when dreams occur, scientists continued debating why dreams exist in the first place. One of the earliest influential psychological theories of dreaming came from Sigmund Freud, whose 1900 book, The Interpretation of Dreams, proposed that dreams represented disguised expressions of unconscious desires and fears. Freud believed that many human impulses, particularly those related to conflict, anxiety, or socially unacceptable desires, were suppressed by the conscious mind during waking life. According to his theory, these hidden impulses could reappear during sleep in symbolic form, allowing the subconscious mind to express itself indirectly. Although Freud's ideas had enormous influence on early psychology, many of his specific interpretations have not been supported by modern scientific evidence. Nevertheless, Freud's work helped draw attention to the role of unconscious processes in shaping mental life. His emphasis on the hidden mind inspired generations of researchers to explore how dreaming might reflect deeper psychological processes. Modern neuroscience offers several possible explanations for why dreams occur. One widely supported theory suggests that dreaming plays a role in memory consolidation. Throughout the day, the brain constantly records new experiences, storing fragments of information within networks of neurons. During sleep, particularly during REM sleep, the brain may replay these experiences, strengthening important connections and integrating new memories with existing knowledge. Brain imaging studies have shown that areas such as the hippocampus, which plays a crucial role in forming memories, remain active during sleep. In experiments involving both animals and humans, patterns of neural activity associated with learning tasks have been observed to reappear during subsequent sleep periods. This replay of neural patterns may help stabilize memories and transfer them into long-term storage. Another theory suggests that dreams help regulate emotional experiences. During waking life, individuals encounter events that trigger strong feelings such as fear, joy, anger, or sadness. Some neuroscientists believe that dreaming provides a safe environment in which the brain can process these emotions and reduce their intensity. Research has shown that REM sleep is associated with decreased levels of certain stress-related neurotransmitters, particularly norepinephrine, which is involved in the brain's response to threat and arousal. This chemical environment may allow the brain to revisit emotional memories without triggering the same level of physiological stress experienced during waking life. Experiments have also demonstrated that people who are deprived of REM sleep often experience increased irritability, difficulty concentrating, and problems with emotional regulation. These findings suggest that dreaming may help maintain psychological balance by allowing the brain to process emotional experiences during sleep. Dreams have also been linked to creativity and problem-solving. Throughout history, numerous scientists, artists, and inventors have described moments of insight that emerged during dreams. One famous example involves the 19th century chemist Auguste Kekulé, who had been struggling to understand the structure of the benzene molecule. According to Kekulé's later account, he dreamed of a snake biting its own tail, a circular image that suddenly inspired him to realize that the benzene molecule might form a ring structure rather than a linear chain. This insight played an important role in advancing the field of organic chemistry. Another well-known story involves Elias Howe, the inventor of the modern sewing machine. Howe reportedly struggled to design a needle that would function effectively in a mechanical sewing device. In a dream, he imagined being captured by warriors carrying spears with holes near their tips. When he awoke, he realized that placing the hole near the tip of the sewing needle would allow the thread to pass through the fabric efficiently. Although such stories are sometimes embellished over time, they illustrate how the brain's creative processes may continue working during sleep. When freed from the constraints of logical reasoning and conscious control, the mind may explore unusual associations that lead to unexpected insights. Among the most fascinating dream-related phenomena is lucid dreaming, a state in which a person becomes aware that they are dreaming while the dream is still occurring. In some cases, lucid dreamers can even influence the events unfolding within the dream, altering the environment or guiding the narrative. During the 1980s, psychologist Stephen LaBerge at Stanford University conducted pioneering research on lucid dreaming. LaBerge demonstrated that lucid dreamers could communicate with researchers from within the dream state by performing predetermined eye movement patterns while asleep. Because eye muscles remain active during REM sleep, these signals could be detected by instruments monitoring eye movements. These experiments confirm that lucid dreamers can maintain a degree of conscious awareness while remaining in the dreaming state, offering a rare glimpse into the boundary between waking consciousness and subconscious dream activity. Perhaps the most dramatic example of subconscious control during sleep occurs in a condition known as sleepwalking, or somnambulism. Individuals experiencing sleepwalking episodes may perform surprisingly complex behaviors while remaining largely unconscious. Some sleepwalkers walk through their homes, open doors, move objects, or even prepare food without waking fully. In rare cases, individuals have been reported to perform highly coordinated actions such as driving vehicles or navigating familiar environments while sleepwalking. These behaviors are guided by automatic neural systems responsible for learned routines and spatial navigation, even though the conscious mind remains disconnected from the experience. Sleepwalking demonstrates how powerful the brain's subconscious systems can be. The same neural circuits that allow people to walk, navigate spaces, and perform familiar tasks during waking life can continue operating even when conscious awareness is largely absent. Dreams therefore reveal that the subconscious mind remains highly active even when the conscious mind appears to be offline. During sleep, hidden memories, emotional associations, and fragments of experience can emerge in vivid symbolic forms. These dream narratives may reflect the brain's attempts to organize memories, process emotions, or explore creative ideas beyond the constraints of waking logic. Despite centuries of fascination and decades of scientific research, dreams remain one of the most mysterious aspects of human experience. Each night, the brain constructs entire worlds of imagery and emotion, while the conscious mind drifts through landscapes that feel both familiar and strange. Yet dreams are only one of the many ways the subconscious mind influences behavior. Even when we are fully awake, hidden mental processes continue shaping our perceptions and decisions in subtle ways. Small cues in the environment, sounds, images, words, or emotional signals can influence how we think and act without ever entering conscious awareness. In the next chapter, we explore these hidden influences and the fascinating science behind subliminal signals, revealing how unseen forces quietly guide our perceptions and decisions throughout everyday life. Chapter 7. The Signals You Never Notice. Long before modern neuroscience began examining subconscious influence inside laboratories, people were already fascinated by the possibility that hidden signals could shape human behavior. The idea that subtle messages might influence the mind without conscious awareness captured the public imagination during the 20th century, particularly in the world of advertising and mass communication. As television, film, and radio became powerful tools capable of reaching millions of people at once, some observers began to wonder whether these media could also be used to influence behavior in ways viewers would never consciously notice. One of the most famous stories connected to this idea emerged in 1957 when a market researcher named James Vickery claimed to have conducted a remarkable experiment in a movie theater in Fort Lee, New Jersey. According to Vickery's announcement, he had installed a device capable of flashing brief messages onto a cinema screen during the film. The messages, "Drink Coca-Cola" and "Eat popcorn," appeared for only a fraction of a second, supposedly too quickly for viewers to consciously perceive them. Vickery claimed that the results were dramatic. In his report, he stated that popcorn sales had increased by nearly 60%, while Coca-Cola sales rose by about 18% during the experiment. The implication was startling. If such tiny flashes of information could influence consumer behavior without viewers realizing it, then hidden messages could potentially be used to manipulate the public on a massive scale. The story spread rapidly through newspapers, magazines, and television broadcasts. Public concern grew as people began to imagine the possibility of invisible persuasion embedded within films, advertisements, or political messages. Some government officials even discussed the possibility of regulating subliminal advertising, fearing that citizens could be influenced without their consent. However, the dramatic claims did not withstand scrutiny. In 1962, Vickery admitted that the data from the experiment had been fabricated. The experiment had never been conducted as he described, and the reported results had no scientific basis. Although the revelation exposed the story as a hoax, the idea of subliminal influence had already taken hold in the public imagination. Rather than abandoning the concept entirely, psychologists and cognitive scientists began investigating whether more subtle forms of unconscious influence might actually exist. If flashing messages on movie screens did not secretly control consumer behavior, perhaps other kinds of hidden cues could still shape thoughts and decisions without conscious awareness. This question led researchers to explore a phenomenon known as priming. Priming occurs when exposure to a particular stimulus influences how a person responds to a later stimulus, even if they are not consciously aware of the connection between the two. In many priming experiments, participants are briefly exposed to certain words, images, or concepts before completing an unrelated task. Researchers then examine whether the earlier exposure subtly influences the participants' responses. Throughout the 1960s and 1970s, psychologists conducted numerous experiments exploring priming effects. In some studies, participants were shown words related to particular concepts before completing puzzles, reading tasks, or decision-making exercises. The results often revealed small but measurable changes in behavior that seemed to reflect the earlier exposure. One widely discussed experiment involved exposing participants to words associated with aging, including terms such as retired, wrinkle, and Florida. After completing the task, participants left the laboratory and walked down a hallway. Researchers measured the time it took them to reach the elevator and found that participants who had been exposed to aging-related words tended to walk slightly more slowly than those who had not seen the words. The interpretation of this experiment was that activating the concept of aging in the subconscious mind might subtly influence behavior. Although this study became famous, it also sparked controversy in later years when some researchers failed to replicate the findings consistently. The debate highlighted an important reality about subconscious influence. While such effects can exist, they are often subtle and sensitive to experimental conditions. Another line of research explored how emotional signals embedded in the environment could shape perception and judgment. Psychologists discovered that human beings are remarkably sensitive to emotional cues conveyed through facial expressions, tone of voice, and body language. These signals can influence reactions even when individuals are not consciously paying attention to them. In a series of experiments conducted during the 1990s, researchers briefly displayed images of faces expressing different emotions, such as happiness or anger, for only a few milliseconds before replacing them with neutral images. Because the emotional faces appeared so quickly, participants typically reported that they had seen only the neutral images. Despite this lack of conscious awareness, the emotional expressions influenced how participants evaluated the neutral images that followed. When exposed to brief flashes of smiling faces, participants tended to rate neutral images more positively. When exposed to angry faces, their evaluations became more negative. Brain imaging studies suggest that this effect may occur because emotional information can be processed by the amygdala, the brain's threat detection and emotional processing center, even when the visual cortex does not produce conscious awareness of the stimulus. In other words, the emotional brain may respond to signals that the conscious mind never notices. Subtle environmental cues can also influence behavior in surprisingly specific ways. Researchers studying consumer psychology have discovered that factors such as color, lighting, and background music can shape how people feel and behave in commercial settings. Color psychology provides a clear example. Different colors often carry emotional associations shaped by both cultural learning and biological responses. Shades of blue are frequently associated with calmness, trust, and reliability, which is why many banks and technology companies incorporate blue into their branding. Red, by contrast, is often associated with urgency, excitement, or danger, making it a common color in sales promotions and warning signs. Sound can also influence behavior in subtle ways. In one well-known experiment conducted in the early 2000s, researchers studied purchasing patterns in a wine shop that alternated between playing French music and German music on different days. When French music played in the background, customers were significantly more likely to purchase French wine. When German music played, German wines became more popular. Interestingly, when customers were later asked whether the music had influenced their decision, most said that it had not. They believed they had chosen their wine independently, even though the environmental cue had clearly shifted purchasing behavior across the store. These kinds of subtle influences demonstrate how the subconscious mind continuously absorbs information from the surrounding environment. While individuals may believe they are making decisions purely through conscious reasoning, hidden cues can shape perceptions and preferences in ways that remain invisible to awareness. Perhaps one of the most powerful demonstrations of subconscious influence appears in the placebo effect, a phenomenon that has become a central topic in modern medicine. The placebo effect occurs when a person experiences genuine improvements in symptoms after receiving a treatment that contains no active medical ingredient. Placebos are commonly used in clinical trials as control treatments to determine whether a new medication is truly effective. In many studies, patients who receive placebo pills, often made of harmless substances like sugar, report significant improvements in pain, mood, or other symptoms simply because they believe they are receiving a real treatment. Remarkably, these improvements are not purely psychological. Brain imaging studies have shown that placebo treatments can trigger measurable physiological changes, including the release of natural pain-relieving chemicals known as endorphins. In some cases, placebo treatments can even alter activity in brain regions associated with pain perception. The placebo effect illustrates the extraordinary influence that expectations can have on the body. When the brain anticipates improvement, the subconscious mind may activate biological systems capable of producing real physical changes. Closely related to the placebo effect is the concept of suggestibility, which plays a major role in hypnosis. Hypnosis has been studied scientifically since the 19th century, when physicians such as James Braid in Scotland began investigating altered states of focused attention and suggestion. During hypnosis, individuals often enter a state of deep concentration in which they become highly responsive to suggestions from a hypnotist. In this state, people may experience changes in perception, memory, or even pain sensitivity. For example, some individuals under hypnosis can undergo medical procedures with reduced pain, responding to suggestions that the discomfort will diminish. Modern brain imaging studies have shown that hypnosis can alter activity in regions associated with attention, perception, and cognitive control. These findings suggest that suggestions delivered during hypnosis may influence subconscious neural processes that shape how sensations are experienced. Together, these discoveries reveal that the human mind is constantly absorbing and interpreting signals from the surrounding environment. Words, images, emotional expressions, sounds, and social cues can all influence how people think and behave, often without ever entering conscious awareness. Most of these influences are relatively small. Subliminal cues do not grant advertisers or governments the ability to control people's actions with hidden commands. However, the research clearly demonstrates that the subconscious mind remains highly sensitive to patterns and associations embedded in everyday experience. Even when we believe we are thinking independently, countless signals are quietly shaping our perceptions, emotions, and decisions behind the scenes. This realization leads to an intriguing question. If the subconscious mind is constantly absorbing information from the environment, where does all of that information go? How does the brain store the countless experiences and associations that influence our behavior over time? The answer lies within one of the brain's most powerful systems, the vast network responsible for memory. In the next chapter, we explore the hidden memory systems that quietly record experiences, shape habits, and influence decisions long after the conscious mind has forgotten the events themselves. Chapter 8. The Memory Beneath Awareness. Human memory is often imagined as a kind of mental archive, a vast internal library where experiences are carefully stored and later retrieved when needed. In everyday conversation, people often describe memories as though they were files placed neatly into storage, waiting patiently to be opened again. Yet, modern neuroscience has revealed that the structure of memory is far more complex than this simple metaphor suggests. Rather than existing as a single storage system, the brain contains multiple interacting forms of memory, many of which operate almost entirely outside conscious awareness. These hidden systems shape skills, emotional reactions, perceptions, and decision-making processes in ways that continue influencing behavior long after the original experiences have faded from conscious thought. One of the most important distinctions in the study of memory is the difference between explicit memory and implicit memory. Explicit memory refers to information that can be consciously recalled and described. These are the memories people typically think of when they speak about remembering something, recalling the details of a birthday party, remembering a historical date, or recognizing the face of a friend. Explicit memories depend heavily on structures within the medial temporal lobe, particularly the hippocampus, which helps organize experiences into memories that can later be consciously retrieved. Implicit memory operates very differently. Instead of producing conscious recollections, implicit memory influences behavior automatically. A person may not consciously remember learning a particular skill or association, yet their actions reveal that the knowledge remains stored somewhere within the brain. Implicit memory can guide movements, shape emotional reactions, and influence perception without ever entering awareness. One of the most familiar forms of implicit memory is procedural memory, which governs learned motor skills. Procedural memory allows individuals to perform complex physical actions without consciously thinking about each step involved. Skills such as riding a bicycle, typing on a keyboard, swimming, or playing a musical instrument rely heavily on procedural memory. When a person first learns a new physical skill, the task requires focused attention and deliberate effort. Each movement must be planned consciously, and mistakes are common. Over time, however, repeated practice gradually transforms the activity into an automatic routine. The brain shifts control of the movements away from conscious planning centers and into deeper neural structures, including the basal ganglia and the cerebellum. Once the skill is encoded in these systems, the body can perform the actions smoothly and efficiently without requiring conscious supervision. Musicians provide a striking example of this process. A beginner learning to play the piano must concentrate intensely on each finger movement, carefully reading notes and translating them into physical actions. An experienced pianist, by contrast, can perform intricate passages while thinking about entirely different aspects of the music, such as emotional expression or tempo. The brain has effectively stored the mechanical aspects of playing within procedural memory systems. One of the most famous demonstrations of the power of implicit memory emerged from the study of a patient known as Henry Molaison, referred to in scientific literature for many years simply as HM. In 1953, Molaison underwent experimental brain surgery in Hartford, Connecticut, in an attempt to treat severe epileptic seizures that had resisted other forms of treatment. During the operation, surgeons removed portions of his medial temporal lobes, including much of the hippocampus, a structure crucial for forming new explicit memories. Although the surgery successfully reduced his seizures, it produced a profound and unexpected side effect. After the operation, Molaison was unable to form new long-term explicit memories. Conversations, events, and experiences faded from his awareness within minutes. Each time someone entered the room, he experienced them almost as though meeting them for the first time. Despite this dramatic loss of conscious memory formation, Molaison retained many other cognitive abilities. Most remarkably, he could still learn new motor skills. In a series of experiments conducted by neuropsychologist Brenda Milner, Molaison practiced a task known as mirror tracing, in which participants must trace the outline of a shape while viewing their hand only through a mirror. The task is challenging at first because the mirror reverses the normal relationship between movement and visual feedback. Over repeated trials, Molaison's performance improved significantly. His hand movements became smoother and more accurate, indicating that his brain was learning the skill. Yet each time he returned to the laboratory, he insisted that he had never performed the task before. The skill had been stored in his brain, but the conscious memory of learning it had vanished. This case provided powerful evidence that different types of memory rely on separate neural systems. Explicit memory requires structures such as the hippocampus, while procedural memory depends on other regions that operate largely outside conscious awareness. Another important aspect of subconscious memory involves emotional associations. Experiences accompanied by strong emotions often leave lasting impressions in the brain's emotional circuitry. The amygdala, a small structure within the limbic system, plays a crucial role in linking emotional responses with memories of events. When a person encounters a situation involving fear, excitement, or joy, the amygdala interacts with memory systems to strengthen the storage of the experience. This process helps the brain learn from emotionally significant events. For example, if a person encounters danger in a particular location, the emotional intensity of the experience increases the likelihood that the memory will influence future behavior. Sometimes these emotional associations remain active even when the original event cannot be consciously recalled. A person might feel uneasy in a particular situation without remembering the experience that created the association. The subconscious emotional memory continues to influence behavior even though the explicit memory has faded. The connection between memory and emotion becomes especially evident in responses triggered by smell. The olfactory system, responsible for processing odors, has unusually direct connections to brain regions involved in emotion and memory, including the amygdala and hippocampus. Unlike many other sensory pathways, which pass through multiple processing stages before reaching emotional centers, smell signals can activate these regions quickly and directly. As a result, certain scents can evoke vivid memories from the distant past. The smell of a particular perfume, a specific food, or even the scent of a familiar environment may suddenly bring back detailed recollections that have remained dormant for years. These sensory cues can trigger emotional responses that feel almost instantaneous, demonstrating how closely memory and perception are intertwined. Psychologists have also explored another phenomenon, revealing how memories can influence perception even when people are not consciously aware of remembering anything. This phenomenon is known as priming. Priming occurs when exposure to a stimulus influences how a person responds to a later stimulus, often without conscious awareness of the connection. For example, if someone briefly sees the word yellow, they may recognize the word banana more quickly moments later. The earlier exposure activates related concepts within the brain's memory networks, making associated ideas easier to process. These effects can occur even when the initial stimulus is presented so briefly that participants do not consciously remember seeing it. Priming demonstrates that the brain continuously retains traces of information that remain active within neural networks. These traces may subtly shape perception and decision-making even when individuals believe they are responding entirely independently. Memory systems also play a central role in pattern recognition, one of the brain's most powerful abilities. Every moment, the brain compares incoming sensory information with stored experiences accumulated over a lifetime. This comparison allows people to recognize faces almost instantly, interpret language rapidly, and navigate complex environments without deliberate analysis. Consider how quickly people can recognize a familiar face in a crowded room. The brain does not analyze each facial feature individually. Instead, it compares the overall pattern of the face with stored representations within memory networks. When a match is detected, recognition occurs almost instantly. This pattern recognition process operates largely outside conscious awareness. The brain performs complex comparisons within fractions of a second, presenting the final result to consciousness as a simple feeling of familiarity. Despite the extraordinary capabilities of memory systems, human memory is far from perfect. Rather than functioning as a precise recording device, memory is constantly being edited, reorganized, and reconstructed. Each time a memory is recalled, it can be subtly altered by new information or by the context in which the recollection occurs. Research conducted by psychologist Elizabeth Loftus has demonstrated just how flexible memory can be. In a series of experiments beginning in the 1970s, Loftus showed that suggestions introduced after an event could influence how people remembered it. Participants who watched videos of traffic accidents, for example, later recalled different details depending on the wording of questions they were asked. When researchers used words such as smashed rather than hit, participants were more likely to remember broken glass that had never actually appeared in the footage. In other experiments, Loftus demonstrated that entirely false memories could sometimes be implanted through suggestion. Participants occasionally became convinced that they had experienced events that never occurred, illustrating how easily memory can be shaped by external influences. These findings highlight an important feature of memory. It is not a static archive, but a dynamic system, constantly integrating new information with past experiences. The subconscious mind plays a major role in shaping how memories are stored, retrieved, and interpreted. Understanding these hidden memory systems reveals just how deeply past experiences influence present behavior. The brain stores countless patterns, emotional associations, and learned skills that guide our actions automatically. When we feel a sudden sense of familiarity, attraction, or discomfort, we may be responding to memories that exist beneath conscious awareness. In many cases, these influences appear in the form of intuitive judgments. A person might feel drawn toward a particular place or uneasy about a situation without fully understanding why. The subconscious mind may be drawing upon stored experiences and associations that never reach conscious thought. Yet memory alone does not determine how people make decisions. Another powerful force shapes human behavior, one that often overrides careful reasoning and logical analysis. This force arises from the brain's emotional systems, which constantly evaluate situations and generate feelings that guide choices. In the next chapter, we explore how these emotional signals influence decision-making, revealing why human choices are often shaped less by rational thought and more by the hidden power of emotion. Chapter 9. Why emotion makes your decisions. For centuries, philosophers often portrayed reason as the primary force guiding human behavior. In many classical traditions, the ideal mind was one that controlled emotion through logic and careful deliberation. Emotions were frequently described as distractions, powerful but unreliable impulses that could cloud judgment and interfere with rational thought. From the writings of Plato to Enlightenment thinkers such as René Descartes, the image of the rational mind overcoming emotional impulses became deeply embedded in Western ideas about human nature. Modern neuroscience, however, has revealed that this traditional picture may be incomplete. Rather than acting as obstacles to clear thinking, emotional signals generated by subconscious brain systems appear to be essential for making even the most ordinary decisions. Far from interfering with rational thought, emotions help guide attention, prioritize options, and assign value to different choices. Without emotional input, the brain's decision-making process can become surprisingly ineffective. One of the most influential discoveries in this area emerged from the work of neuroscientist Antonio Damasio at the University of Iowa during the late 20th century. Damasio became interested in how specific brain regions contribute to decision-making, particularly in patients who had suffered damage to areas involved in emotional processing. Among the brain regions he studied was the ventromedial prefrontal cortex, a portion of the frontal lobe located just behind the forehead. This region plays an important role in integrating emotional signals with higher cognitive processes such as planning, reasoning, and evaluating consequences. Damage to this area can produce subtle yet profound changes in how individuals make decisions. Damasio observed that some patients with injuries to the ventromedial prefrontal cortex appeared outwardly normal in many respects. Their intelligence remained intact, and they could perform well on standard tests of memory, language, and reasoning. When presented with hypothetical scenarios, these individuals could analyze situations logically and explain the possible outcomes of different choices. Yet despite these preserved abilities, their real-world decision-making often deteriorated dramatically. One of Damasio's most well-known patients, referred to in scientific literature as Elliot, demonstrated this phenomenon vividly. In the early 1980s, Elliot underwent surgery to remove a tumor that had developed near the frontal lobes of his brain. Although the operation successfully eliminated the tumor and preserved his general intellectual abilities, it also damaged regions associated with emotional processing. After the surgery, Elliot's personality and behavior changed in subtle but significant ways. He remained capable of logical reasoning and could discuss complex issues with impressive clarity. However, when confronted with everyday decisions, he often struggled to reach conclusions. Tasks that once required only a few moments of thought now consumed large amounts of time and mental effort. For example, Elliot might spend hours carefully weighing minor details while attempting to decide where to schedule an appointment or which of several options to choose for a routine activity. Even trivial decisions could become exhausting exercises in analysis. Without emotional signals to help prioritize alternatives, the process of evaluating choices seemed to stall. Over time, these difficulties began affecting his life more seriously. Despite his intellectual abilities, Elliot struggled to maintain employment and manage practical responsibilities. The absence of emotional guidance had left his reasoning intact but strangely ineffective in guiding behavior. Observations like these led Damasio to develop an influential theory known as the somatic marker hypothesis. According to this idea, emotional responses generated by the body and brain serve as markers that attach positive or negative value to different options. These emotional signals arise from previous experiences and help guide decision-making by narrowing the range of possibilities that need to be considered. The term somatic refers to the body, reflecting Damasio's belief that emotional signals often involve physiological changes such as shifts in heart rate, muscle tension, or hormonal activity. When the brain evaluates potential actions, these bodily signals help indicate which options are likely to lead to beneficial outcomes and which may involve risk or danger. In essence, emotional responses function as shortcuts within the decision-making process. Instead of analyzing every possible consequence of every option, the brain uses emotional markers to quickly identify choices that feel promising or threatening. These signals allow individuals to focus their attention on the most relevant possibilities while ignoring less important alternatives. Damasio and his colleagues tested this idea using an experimental task known as the Iowa gambling task, which was designed to simulate real-world decision-making under uncertain conditions. In the task, participants were presented with 4 decks of cards and asked to select cards repeatedly in order to win money. Each card produced either a reward or a penalty, and the goal was to maximize overall profit. 2 of the decks offered relatively small rewards but also small penalties, making them advantageous in the long run. The other 2 decks provided larger immediate rewards but occasionally imposed heavy losses that ultimately produced negative outcomes over time. At the beginning of the experiment, participants did not know which decks were beneficial and which were risky. As the task progressed, healthy participants gradually learned to avoid the disadvantageous decks even before they could consciously explain the pattern of rewards and losses. What made the experiment particularly interesting was the measurement of physiological responses during the task. Researchers monitored participants' skin conductance, a measure of subtle changes in sweat gland activity associated with emotional arousal. These changes are often referred to as anticipatory stress responses. Remarkably, the skin conductance measurements began increasing when participants considered selecting cards from risky decks before they were consciously aware that those decks were dangerous. In other words, their bodies were reacting to the negative patterns before their conscious reasoning had fully recognized them. Participants with damage to emotional processing regions such as the ventromedial prefrontal cortex behaved very differently. These individuals did not develop the anticipatory stress responses seen in healthy participants. As a result, they continued selecting cards from the risky decks even after experiencing repeated losses. The findings suggested that emotional signals generated by subconscious brain systems were guiding decisions long before conscious reasoning entered the process. The emotional brain appeared to detect patterns of risk and reward and transmit warning signals that influenced behavior. Emotion also plays a crucial role in motivation, another essential component of decision-making. The brain contains reward systems involving neurotransmitters such as dopamine, which help reinforce behaviors associated with positive outcomes. When individuals experience pleasure or success, dopamine pathways within regions such as the ventral striatum and nucleus accumbens become active, strengthening neural connections associated with the behavior that produced the reward. These chemical signals encourage individuals to repeat actions that have previously led to beneficial outcomes. Without such reinforcement systems, the brain would struggle to determine which behaviors are worth pursuing. Fear provides another powerful example of how subconscious emotional systems guide behavior. When the brain detects a potential threat, the amygdala initiates a rapid cascade of physiological responses that prepare the body for action. Heart rate increases, muscles tense, and attention becomes sharply focused on the source of danger. These reactions occur within fractions of a second and often precede conscious recognition of the threat. From an evolutionary perspective, this rapid emotional response system was essential for survival. Early humans living in unpredictable environments could not afford to pause and analyze every potential danger. The ability to react instantly to threatening stimuli greatly increased the chances of avoiding predators or other hazards. Emotional influences also shape decision-making in ways that extend beyond immediate survival. In the field of behavioral economics, researchers have shown that people often rely on emotional impressions rather than careful calculations when evaluating risks and rewards. Psychologist Daniel Kahneman, who received the Nobel Prize in Economics in 2002, described this process as the interaction between two modes of thinking. The first mode operates quickly and automatically, relying on intuition and emotional impressions. The second mode functions more slowly and deliberately, engaging analytical reasoning and conscious evaluation. In many situations, the fast emotional system produces immediate judgments that guide behavior long before the slower analytical system becomes involved. While the analytical system can sometimes override emotional impulses, it often accepts the conclusions generated by the faster system. These findings suggest that emotion is not merely an accessory to rational thought, but an integral component of the brain's decision-making machinery. Emotional signals generated by subconscious systems continuously evaluate situations, prioritize information, and guide attention toward options that appear promising or dangerous. Without these signals, decision-making becomes extremely difficult. The experiences of patients like Elliot demonstrate that reasoning alone is often insufficient to guide behavior effectively. Emotional input provides the brain with the value signals necessary to navigate complex choices. The more scientists explore the relationship between emotion and decision-making, the clearer it becomes that many of our choices emerge from interactions between conscious reasoning and subconscious emotional systems. Thoughts and feelings intertwine in ways that shape behavior long before we become aware of the underlying processes. These discoveries raise an increasingly profound question. If subconscious systems generate emotional signals, process memories, predict outcomes, and even begin preparing decisions before conscious awareness appears, then what exactly is the role of the conscious mind in guiding behavior? In the next chapter, we confront one of the most debated ideas in modern neuroscience and philosophy: the possibility that the experience of free will may be more limited, or perhaps more mysterious, than we have traditionally believed. Chapter 10. The Illusion of Free Will. For thousands of years, philosophers have wrestled with one of the most enduring questions about human nature. Do people truly possess free will, or are their actions determined by forces beyond their control? Ancient thinkers debated whether human beings are genuinely free agents capable of choosing their own paths, or whether every decision emerges from prior causes that shape behavior long before the moment of choice arrives. In ancient Greece, philosophers such as Aristotle argued that rational choice lies at the core of human identity. According to this view, the ability to deliberate about options and select among them defines what it means to be human. Yet other thinkers offered a more deterministic perspective. The 17th century philosopher Baruch Spinoza, for example, argued that human actions follow natural laws just as physical objects do, suggesting that the feeling of freedom may arise simply because people are unaware of the forces influencing their behavior. For centuries, this debate remained largely philosophical, grounded in reasoning rather than direct observation. However, modern neuroscience has introduced new tools capable of examining how decisions unfold inside the brain itself. By measuring neural activity associated with perception, emotion, and action, scientists have begun exploring how much control the conscious mind truly has over human behavior. The results of these investigations have produced insights that challenge some of our most deeply held assumptions about the nature of choice. One of the most intriguing clues about the brain's role in shaping decisions emerged from research on patients who had undergone a rare surgical procedure known as a corpus callosotomy. This operation was occasionally performed in the mid-20th century as a treatment for severe epilepsy that could not be controlled through medication. The procedure involved cutting the corpus callosum, the thick bundle of nerve fibers connecting the left and right hemispheres of the brain. By severing this connection, surgeons hoped to prevent epileptic seizures from spreading between the hemispheres. Although the surgery often reduced the severity of seizures, it produced an unusual neurological condition that became known as the split brain phenomenon. In split brain patients, the two hemispheres of the brain could no longer communicate directly with one another. Because each hemisphere processes information from the opposite side of the visual field and controls different aspects of behavior, this separation created a unique opportunity for scientists to study how the brain interprets and explains its own actions. During the 1960s and 1970s, neuroscientist Roger Sperry and later psychologist Michael Gazzaniga conducted a series of pioneering experiments with split-brain patients. These experiments revealed surprising insights about how the brain constructs explanations for behavior. Researchers discovered that when visual information was presented to only one hemisphere of the brain, the patient's responses depended on which hemisphere received the information. For example, when an image was flashed briefly in the left visual field, the information traveled primarily to the right hemisphere of the brain. In most individuals, the right hemisphere does not control speech, which is typically dominated by the left hemisphere. As a result, when patients were asked what they had seen, they often responded that they had seen nothing. Yet when asked to point to an object related to the image using their left hand, which is controlled by the right hemisphere, they could select the correct item with surprising accuracy. The most fascinating aspect of these experiments emerged when researchers asked patients to explain their choices. Because the speaking left hemisphere did not have access to the information presented to the right hemisphere, it had no direct knowledge of why the left hand had chosen a particular object. Nevertheless, the brain frequently generated an explanation anyway. One well-known experiment illustrates this phenomenon vividly. In the study, researchers presented two different images simultaneously, one to each hemisphere of the brain. The left hemisphere was shown a picture of a chicken claw, while the right hemisphere was shown a snowy landscape. Afterward, the patient was asked to choose related images from a set of pictures placed on a table. The patient's right hand, controlled by the left hemisphere, selected a picture of a chicken, which logically corresponded to the chicken claw image. At the same time, the left hand, controlled by the right hemisphere, selected a picture of a shovel, presumably related to the snowy landscape. When the researchers asked the patient to explain the selections, the speaking left hemisphere was aware only of the chicken image. Yet rather than admitting ignorance about the shovel choice, the brain constructed a plausible explanation. The patient calmly replied that the chicken claw went with the chicken and that the shovel was needed to clean out the chicken coop. In reality, the shovel had been selected because the right hemisphere had seen the snowy landscape and associated the shovel with snow. However, the speaking hemisphere lacked access to that information. Instead of acknowledging the gap in knowledge, it created a logical story that made the behavior appear coherent. Michael Gazzaniga described this phenomenon as the work of the brain's interpreter. According to his theory, the left hemisphere contains neural systems specialized for constructing explanations and narratives that make sense of behavior. This interpreter continuously attempts to create a coherent story about why actions occur, even when the true causes lie outside conscious awareness. The existence of this interpretive system suggests that the conscious mind may not always be directing actions as much as explaining them. The brain appears capable of generating convincing narratives about behavior even when the underlying causes remain hidden. This insight resonates strongly with the findings from earlier experiments on decision-making. Studies such as Benjamin Libet's readiness potential experiments and later brain imaging research suggest that neural activity related to decisions can begin forming before conscious awareness appears. In those experiments, patterns of brain activity predicting actions emerged hundreds of milliseconds, or even several seconds, before participants reported becoming aware of deciding. When these findings are considered together, they suggest that the conscious experience of choosing may occur after the brain has already begun preparing the action. The mind may experience the decision as a deliberate choice, but the neural machinery responsible for initiating the action may have already set the process in motion. Some philosophers and scientists interpret these results as evidence that traditional ideas about free will may need to be reconsidered. If subconscious brain processes initiate decisions before conscious awareness enters the picture, then the feeling of deliberate control might arise from the brain interpreting its own activity rather than directing it from the beginning. Others argue that these findings do not eliminate free will entirely, but instead suggest that free will operates differently than we once imagined. According to this perspective, conscious awareness may still play an important role in shaping behavior, perhaps by evaluating impulses generated by subconscious systems and deciding whether to allow them to proceed. This interpretation echoes Benjamin Libet's idea of the veto power of consciousness. Although subconscious neural processes may initiate potential actions, the conscious mind may retain the ability to stop those actions before they are carried out. In this sense, consciousness may function more as a supervisory system than as the original source of decisions. There are also evolutionary reasons why the brain might generate the experience of conscious agency. The sense that we are responsible for our actions plays a crucial role in social life. Human societies depend heavily on concepts such as responsibility, accountability, and moral judgment. If individuals did not feel that they were the authors of their own actions, it would be difficult to maintain systems of cooperation and trust. From this perspective, the experience of free will may serve an important psychological and social function. Even if decisions arise from complex interactions among subconscious neural systems, the sense of agency helps individuals navigate social environments, learn from consequences, and take responsibility for their behavior. Modern neuroscience has therefore not resolved the ancient debate about free will. Instead, it has transformed the discussion by shifting attention toward the mechanisms underlying decision-making. Rather than asking whether humans possess free will in an abstract philosophical sense, researchers increasingly investigate how conscious and subconscious systems interact within the brain. Decisions appear to emerge from dynamic interactions among multiple neural processes, including emotional signals, predictive models, memory networks, and environmental influences. The conscious mind experiences only a portion of this activity, often becoming aware of decisions after they have already begun forming within deeper brain systems. This evolving scientific perspective raises an intriguing possibility. If the subconscious mind plays such a central role in shaping perception, emotion, memory, and decision-making, then individual consciousness may represent only the surface of a much larger cognitive system operating beneath awareness. As researchers continue exploring these hidden mechanisms, another fascinating question begins to emerge. If human minds rely so heavily on subconscious patterns shaped by shared evolutionary history and similar neural architectures, could there also be deeper patterns connecting human thought across cultures and generations? In the next chapter, we explore the idea that certain symbols, stories, and emotional themes appear repeatedly throughout human history, raising the possibility that the subconscious mind may reflect patterns shared by humanity as a whole. Chapter 11. The patterns shared by every mind. Throughout history, human cultures separated by vast distances and centuries of time have produced remarkably similar myths, symbols, and stories. Ancient civilizations in Egypt, Greece, India, China, and the Americas all developed narratives about heroic journeys, cosmic struggles between order and chaos, wise guides, powerful mothers, tricksters, and shadowy adversaries. These stories emerged long before modern communication connected distant cultures, yet their themes often resemble one another in striking ways. The repetition of these symbolic patterns has fascinated historians, psychologists, and anthropologists for generations, raising an intriguing question about the nature of the human mind. If societies evolve independently across the globe, why do their stories so often follow the same underlying structures? One of the thinkers most captivated by this mystery was the Swiss psychiatrist Carl Jung, who in the early 20th century proposed one of the most ambitious theories about the subconscious mind ever developed. Jung had trained under the founder of psychoanalysis, Sigmund Freud, but eventually developed his own ideas about the deeper layers of human psychology. While Freud focused primarily on the personal unconscious, hidden memories, desires, and conflicts shaped by an individual's life experiences, Jung believed that something even deeper existed beneath the surface of the psyche. According to Jung, the human mind contains not only a personal unconscious formed through individual experience, but also a deeper layer he called the collective unconscious. This hypothetical structure, he suggested, represents a reservoir of inherited psychological patterns shared by all human beings. Rather than consisting of memories or experiences from one's own life, the collective unconscious would contain fundamental symbolic structures that shape how humans perceive the world. Jung proposed that these structures appear in the form of archetypes, universal patterns of thought and imagery that manifest in myths, dreams, and cultural narratives across societies. Archetypes, in Jung's view, function like psychological templates, organizing experiences into recognizable symbolic forms that appear again and again throughout human storytelling. Among the archetypes Jung identified were figures such as the hero, the wise old man, the great mother, the trickster, and the shadow. Each of these symbolic roles represents aspects of human experience that appear repeatedly across cultures. The hero embodies courage and transformation, often embarking on a journey that involves trials, growth, and eventual return. The wise old figure represents knowledge and guidance, offering insight that helps the hero navigate challenges. The shadow symbolizes hidden fears, destructive impulses, or darker elements of the psyche that must be confronted and integrated. These archetypal figures appear not only in ancient myths, but also in modern literature and popular storytelling. The structure of the hero's journey, for instance, can be found in narratives ranging from the ancient Greek epic of Odysseus to modern cinematic stories such as Star Wars or The Lord of the Rings. In each case, the protagonist leaves an ordinary world, encounters trials and mentors, gains knowledge or power, and ultimately returns, transformed by the experience. Jung believed that these patterns persist because they reflect deep psychological structures shared by all humans. According to his theory, the collective unconscious influences how individuals interpret experiences and construct meaning, guiding the creation of symbolic narratives that appear similar even when cultures develop independently. Jung's ideas gained considerable influence during the 20th century, particularly in fields such as psychology, literature, and anthropology. Scholars studying mythology began noticing that many traditional stories share similar narrative structures despite emerging in different cultural environments. One of the most influential figures to explore this idea further was the American mythologist Joseph Campbell. In his widely known 1949 book, The Hero with a Thousand Faces, Campbell examined myths and legends from cultures around the world and argued that many of them follow a common narrative structure that he called the monomyth or the hero's journey. According to Campbell, the hero's journey typically involves a sequence of stages: the call to adventure, the crossing of a threshold into an unfamiliar world, encounters with mentors and adversaries, a climactic ordeal, and finally, a return home transformed by the experience. Campbell's analysis revealed remarkable parallels among stories from cultures separated by oceans and centuries. Ancient Mesopotamian epics, Greek myths, Buddhist legends, and indigenous American narratives all contain variations of similar themes. These similarities raise the possibility that human storytelling may emerge from shared psychological tendencies rather than purely local traditions. Not all scholars agree with Jung's interpretation of these patterns. Many anthropologists argue that the similarities among myths may arise from shared aspects of human life rather than inherited psychological structures. Every society must confront fundamental experiences such as birth, growth, conflict, cooperation, aging, and death. Stories that explore these universal challenges may naturally converge toward similar themes. Another explanation involves cultural transmission. Throughout history, trade routes, migration, and exploration allowed ideas to spread between civilizations. Myths and symbolic imagery may have traveled across continents through storytelling traditions that gradually blended with local cultures. Yet even when these possibilities are taken into account, some researchers believe the human brain itself may predispose people to interpret experiences in particular symbolic ways. Evolutionary psychology, a field that examines how natural selection shaped human cognition, suggests that the brain evolves specialized mechanisms for recognizing social roles, detecting threats, forming alliances, and constructing narratives about identity and purpose. From this perspective, archetypal patterns may arise not because humans inherit specific mythic images, but because the brain is structured to organize experiences into meaningful social narratives. Stories about heroes, mentors, rivals, and transformations reflect the types of relationships and challenges humans have faced throughout evolutionary history. Evidence for shared psychological patterns also appears in the study of dreams. Across many cultures, people report remarkably similar dream themes. Psychologists have documented recurring dream scenarios involving falling from great heights, being chased by unknown figures, arriving late for important events, losing teeth, or wandering through unfamiliar landscapes. While the details of these dreams vary from person to person, the emotional experiences they convey, fear, uncertainty, anticipation, or loss of control, are often strikingly consistent. Some researchers believe these common dream patterns reflect the brain's tendency to process emotional challenges during sleep. Because humans across cultures encounter similar forms of stress and uncertainty, their dreams may naturally organize these experiences into comparable symbolic scenarios. Modern neuroscience has begun exploring another dimension of shared mental patterns, the ways in which human minds influence one another through communication and culture. Ideas spread across societies through language, imitation, and shared narratives, creating networks of influence that shape beliefs and behaviors. Cultural traditions, stories, and symbols can propagate through communities in ways that resemble the spread of information through biological systems. In the modern world, digital communication has dramatically accelerated this process. Through social media platforms and global information networks, ideas can circulate across continents within minutes. Memes, narratives, and symbolic imagery can spread through millions of minds, creating shared patterns of thought on a global scale. Although Jung's original concept of the collective unconscious remains controversial within modern psychology, the persistence of shared symbolic patterns across human societies continues to intrigue researchers. Whether these similarities arise from inherited psychological structures, shared evolutionary experiences, or cultural exchange, they highlight the remarkable ways in which human minds often converge upon similar interpretations of the world. These patterns suggest that the mind is not merely an isolated processor of information contained within the boundaries of an individual brain. Instead, it exists within a broader web of biological evolution, cultural tradition, and shared human experience. Stories, symbols, and emotional themes flow across generations, linking individual consciousness to a larger tapestry of collective meaning. Yet even as scientists explore these connections, one profound mystery remains at the center of all research on the mind. Beneath memory, emotion, perception, and decision-making lies a deeper question that has challenged philosophers and scientists alike. What exactly is the phenomenon that allows humans to experience thoughts, sensations, and awareness in the first place? In the next chapter, we turn to this extraordinary question and explore one of the greatest unsolved problems in science, the origin and nature of consciousness itself. Chapter 12. The Greatest Mystery: Consciousness. Despite centuries of philosophical inquiry and decades of modern neuroscience research, scientists still cannot fully explain one of the most fundamental aspects of human existence: consciousness. Every moment of waking life unfolds through a stream of subjective experience, colors and sounds, thoughts and emotions, memories and sensations. We perceive the world, reflect on our own thoughts, and experience the feeling of being present in time. Yet the biological processes that produce this inner experience remain deeply mysterious. The brain is a physical object composed of neurons, electrical signals, and chemical interactions. Somehow, from this intricate biological machinery, a private world of awareness emerges. This puzzle has challenged thinkers for thousands of years. Philosophers in ancient India and Greece debated the nature of awareness long before modern science developed tools capable of studying the brain itself. Later philosophers in Europe, such as René Descartes, proposed that consciousness might represent a fundamentally different kind of substance from physical matter. Although modern science has largely rejected the idea of a separate, immaterial mind, the question remains unresolved. How can physical processes inside the brain produce the subjective experience of being aware? In the 1990s, philosopher David Chalmers introduced a phrase that has since become widely known in discussions of consciousness: the hard problem of consciousness. The term refers to the difficulty of explaining why certain physical processes give rise to subjective experience. Neuroscience has made enormous progress in understanding how the brain processes information, controls behavior, and integrates sensory signals. Scientists can observe neurons firing, track networks communicating across the brain, and measure electrical patterns associated with perception and attention. Yet even if researchers could map every neural event occurring in the brain, an essential question would remain unanswered. Why should these processes produce a feeling of experience at all? Why does the brain not simply operate like a sophisticated machine that processes information without awareness? Consider the example of color perception. When light of a particular wavelength enters the eye, specialized cells in the retina convert the signal into electrical impulses that travel through the optic nerve to the visual cortex. Neuroscience can describe this entire pathway in extraordinary detail. Yet the explanation still leaves something unexplained. The experience of seeing the color red. The sensation itself, the subjective quality of redness, cannot easily be described in terms of electrical signals or neural circuits. Philosophers sometimes refer to these subjective qualities as qualia, a term used to describe the raw elements of experience such as colors, sounds, or sensations. The existence of qualia highlights the gap between objective descriptions of brain activity and the subjective nature of awareness. A scientist can measure neural activity associated with pain, but the actual feeling of pain can only be experienced from within the mind itself. In response to this challenge, scientists and philosophers have proposed a variety of theories attempting to explain how consciousness might arise from physical systems. One of the most influential modern proposals is integrated information theory, often abbreviated as IIT. This theory was developed by neuroscientist Giulio Tononi at the University of Wisconsin-Madison and later expanded through collaborations with researchers studying neural complexity. Integrated information theory begins with the observation that conscious experiences appear unified. At any given moment, a person's perception of the world feels like a single integrated scene rather than a collection of independent fragments. Sight, sound, emotion, memory, and thought combine into a coherent experience. IIT proposes that this unity reflects the way information is processed within the brain. According to the theory, consciousness arises when information within a system becomes highly integrated, meaning that the system processes information as a unified whole rather than as separate independent parts. When different components of a system interact so strongly that the state of each part depends on the others, the system possesses a high level of integrated information. IIT suggests that the degree of consciousness corresponds to the amount of integrated information present within the system. In this framework, the human brain produces rich conscious experience because billions of neurons interact within complex networks that integrate information across multiple regions. Other systems with less integration may produce simpler forms of awareness, while systems lacking integration entirely would remain unconscious. Another influential approach to understanding consciousness is the global workspace theory, first proposed by cognitive scientist Bernard Baars in the late 20th century and later expanded by neuroscientists such as Stanislas Dehaene. This theory describes consciousness as a kind of information-sharing system within the brain. According to global workspace theory, many cognitive processes occur simultaneously outside conscious awareness. Different brain systems analyze sensory input, evaluate emotional significance, retrieve memories, and prepare potential actions. Most of these processes operate in parallel without entering conscious experience. Consciousness, in this model, arises when certain information becomes globally available to multiple brain systems at once. When a particular piece of information, such as a visual image or a thought, enters the global workspace, it is broadcast across a network of neural regions involved in attention, memory, decision-making, and language. This broadcasting process allows the information to influence multiple cognitive systems simultaneously. The theory compares consciousness to a spotlight on a stage. Many actors and events may exist behind the scenes, but only those illuminated by the spotlight become visible to the audience. Similarly, countless subconscious processes occur within the brain, but only a small portion becomes accessible to conscious awareness at any given moment. While theories like IIT and global workspace theory attempt to explain how consciousness might arise from neural activity, some researchers have proposed even more unconventional possibilities. One of the most controversial ideas to gain renewed attention in recent years is panpsychism, the philosophical view that consciousness may be a fundamental property of the universe. Panpsychism suggests that some form of proto-consciousness may exist in all matter, even at the level of elementary particles. According to this perspective, consciousness does not suddenly appear only in complex brains, but instead emerges from simpler forms of experience that combine and evolve into more sophisticated awareness. Although this idea may seem unusual, some philosophers argue that it offers a potential solution to the hard problem by suggesting that consciousness is not something produced by matter, but rather something intrinsic to it. Another intriguing perspective, known as the filter theory of consciousness, suggests that the brain may not generate consciousness directly, but instead regulate or filter a broader field of awareness. This idea has historical roots in the writings of philosopher and psychologist William James during the 19th century. According to the filter theory, the brain might function as a kind of interface that restricts and organizes a more expansive form of consciousness. Some researchers exploring altered states of consciousness, including meditation, psychedelic experiences, and near-death experiences, have occasionally revisited this idea as a possible explanation for unusual mental phenomena. However, the filter theory remains speculative and controversial, and most neuroscientists continue focusing on explanations rooted in neural processes. Despite the diversity of these theories, scientists have made substantial progress in identifying brain networks associated with conscious states. Advances in functional magnetic resonance imaging, fMRI, and electroencephalography, EEG, have allowed researchers to observe patterns of activity correlated with awareness, attention, and self-reflection. Studies of patients under anesthesia, in comas, or in vegetative states have helped scientists identify neural signatures associated with the presence or absence of consciousness. For example, research has revealed that conscious awareness appears closely linked to interactions among regions of the prefrontal cortex, parietal cortex, and other areas involved in attention and information integration. These networks appear to coordinate information from multiple sensory and cognitive systems, creating the unified experience characteristic of conscious thought. Yet even with these sophisticated tools, an essential limitation remains. Neuroscientists can measure the physical processes associated with consciousness, but they cannot directly measure the experience itself. Brain scans can reveal patterns of neural activity, but they cannot capture the subjective feeling of seeing a sunset, hearing music, or remembering a childhood moment. This challenge reflects a deeper philosophical difficulty in studying consciousness. Consciousness is not only the subject of investigation, it is also the very medium through which all investigation occurs. Every scientific observation ultimately depends on the awareness of the observer. As a result, the attempt to study consciousness involves a unique kind of circularity, the mind attempting to understand itself. Because of this challenge, many researchers believe that understanding consciousness may require interdisciplinary approaches that combine neuroscience, psychology, philosophy, computer science, and even physics. The mystery of consciousness lies at the intersection of multiple scientific domains, and solving it may demand entirely new ways of thinking about the relationship between matter and experience. When we reflect on the discoveries explored throughout this journey, from subconscious perception and predictive processing to emotional decision-making and cultural archetypes, a remarkable pattern emerges. The conscious mind, which feels so central to our identity, may represent only a small visible portion of a vast and intricate mental system. Beneath the surface of awareness lies an immense network of subconscious processes interpreting sensory information, predicting future events, shaping emotional responses and guiding behavior long before the conscious mind becomes aware of them. These hidden systems operate continuously, weaving together memories, perceptions, and expectations to construct the experience we recognize as the self. In many ways, consciousness may resemble the visible crest of a wave rising above the surface of the ocean. Beneath that crest lies an immense depth of unseen motion shaping the movement of the water. Similarly, the thoughts we experience directly may represent only the surface expression of deeper neural processes unfolding within the brain. In the end, the greatest mystery may not simply be whether the subconscious mind influences our lives. The evidence strongly suggests that it does. The deeper question is how such an extraordinary system emerged in the first place. Somewhere within the evolutionary history of the universe, matter organized itself into structures capable of perception, memory, prediction, and reflection. From simple molecules arose cells, from cells arose nervous systems, and from those systems emerged brains capable of constructing an inner world of experience. Within that intricate network of neurons and signals, something extraordinary occurred. Matter became aware of itself, and within that system, the conscious mind watches the world unfold, often unaware of the vast hidden processes guiding every thought, emotion, and decision. Chapter 13. The System Behind the Self. By the time we reach the end of this journey through the subconscious mind, a striking realization begins to take shape. The mind we experience every moment, the quiet voice narrating our thoughts, the feeling that we are choosing our actions, the sense that we are steering the course of our lives, may represent only the outermost layer of a much larger system operating beneath the surface. Conscious awareness feels central to our identity because it is the part we experience directly, yet modern research increasingly suggests that much of the real work of the mind happens elsewhere. Beneath the stream of thoughts we notice lies an intricate network of processes constantly interpreting the world, predicting future events, evaluating emotional significance, and preparing actions long before those processes ever rise into awareness. Over the past century, discoveries in psychology and neuroscience have steadily illuminated the scope of these hidden systems. Early psychologists suspected that the unconscious mind might influence behavior, but the full extent of its activity remained difficult to measure. With the development of modern brain imaging technologies, researchers began observing neural activity unfolding in real time. These tools revealed that the brain continuously processes enormous amounts of information outside conscious awareness. Patterns associated with decisions can appear in neural circuits before a person reports having made a choice. Emotional signals begin influencing behavior before the conscious mind has time to analyze the situation. Even the perception of the world itself emerges from layers of processing that occur largely outside awareness. Experiments studying decision-making provide some of the most revealing examples of this hidden activity. When scientists measure electrical or metabolic signals in the brain, they sometimes observe neural preparations for movement or choice appearing fractions of a second, or even several seconds, before individuals report the moment they consciously decided to act. Although the interpretation of these findings remains debated, they strongly suggest that the process of decision-making begins within subconscious systems that operate before the conscious mind becomes aware of the outcome. These subconscious systems are not simple or isolated mechanisms. Instead, they form a complex network of interacting processes that continuously evaluate information from the environment and from within the body. Sensory systems gather enormous streams of data about the surrounding world. Patterns of light, vibrations of sound, chemical signals from smell and taste, pressure from touch, and internal signals related to hunger, fatigue, or stress. Yet only a small fraction of this sensory information ever reaches conscious awareness. The rest is analyzed and filtered by neural circuits that determine which details deserve attention and which can safely remain unnoticed. This filtering process is essential for survival. If the brain attempted to present every sensory signal to consciousness simultaneously, the mind would be overwhelmed almost instantly. Instead, subconscious networks perform a form of triage, rapidly evaluating incoming information and highlighting what appears most relevant to the organism's goals and safety. The conscious mind experiences the result of this filtering process rather than the full complexity of the underlying analysis. Memory systems contribute another powerful layer to this hidden architecture. Experiences from the past do not simply disappear once they fade from conscious recollection. Instead, they are encoded within vast networks of neural connections that influence behavior in subtle ways. Emotional memories can shape instincts and preferences long after the original events have been forgotten. Skills acquired through repetition become embedded in procedural memory, allowing actions to unfold automatically without deliberate planning. Everyday activities illustrate the importance of these subconscious memory systems. Walking across a room, typing on a keyboard, driving a familiar route, or speaking a native language all depend on patterns stored in neural circuits that function automatically once they are learned. Without these systems, even the simplest actions would require constant conscious attention. Life would become an exhausting sequence of deliberate decisions rather than the fluid stream of behavior we normally experience. The brain's predictive systems add yet another dimension to the subconscious machinery, guiding human behavior. As researchers studying predictive processing have proposed, the brain does not merely react to incoming sensory signals. Instead, it continuously generates expectations about what will happen next. By comparing these predictions with actual sensory input, the brain updates its internal models of the world and prepares responses before events fully unfold. This predictive ability allows humans to navigate complex environments with remarkable efficiency. When catching a ball, interpreting speech, or crossing a busy street, the brain anticipates the likely trajectory of events and prepares actions accordingly. These predictions occur so quickly that conscious awareness often notices only the final result. The sense that perception unfolds smoothly and naturally arises because subconscious systems are constantly forecasting the future and adjusting behavior to match those expectations. Emotion also plays a central role in shaping the decisions that appear to emerge within consciousness. Emotional circuits deep within the brain evaluate potential rewards and threats with extraordinary speed. When a situation appears promising or dangerous, these systems generate signals that influence attention and motivation. The conscious mind experiences these signals as feelings, subtle impressions that something feels right or wrong, safe or risky, appealing or uncomfortable. These emotional cues often guide choices before conscious reasoning has time to evaluate every possibility. Rather than analyzing all available information in detail, the brain relies on emotional markers shaped by past experience to narrow the field of options. In many cases, these subconscious evaluations lead to remarkably effective decisions. At other times, they can produce biases or errors, reminding us that the subconscious mind, while powerful, is not infallible. When all of these processes are considered together, perception, memory, prediction, emotion, and decision-making, a compelling picture begins to emerge. The mind may not operate as a single centralized controller directing behavior from the top down. Instead, it appears more like a dynamic system composed of many interacting components, each contributing specialized functions to the overall operation of the brain. This perspective has led some scientists and philosophers to rethink the nature of the self. Rather than representing a fixed entity located in a specific part of the brain, the self may arise from the coordination of numerous neural processes working together. Different networks handle different aspects of experience. Visual regions interpret incoming light signals, emotional circuits evaluate meaning and relevance, memory systems retrieve past experiences, and predictive mechanisms anticipate future events. The experience of being a unified individual may emerge when these systems synchronize their activity. When perception, memory, emotion, and intention align, the mind constructs the impression of a coherent self moving through the world. In this sense, the self may function less like a central command center and more like a narrative emerging from the cooperation of multiple brain systems. The brain's storytelling ability plays a crucial role in maintaining this sense of unity. Studies of split-brain patients have shown that the mind often constructs explanations for actions, even when it lacks access to the underlying causes. The brain's interpretive systems weave together perceptions and behaviors into a narrative that feels continuous and meaningful. This narrative creates the feeling that our actions flow from a single, coherent identity. Without this interpretive system, experience might feel fragmented. Thoughts, sensations, and impulses could appear disconnected from one another. Instead, the brain's narrative machinery organizes events into a story that allows individuals to understand themselves as agents moving through time. Yet even if the sense of self emerges from complex neural processes rather than from a single controlling entity, the experience remains deeply meaningful. The mind's ability to integrate perception, memory, imagination, and emotion allows humans to create art, develop scientific theories, build civilizations, and reflect on their own existence. The same systems that quietly guide everyday behavior also enable creativity, curiosity, and the search for understanding. As scientific research continues to explore the brain, new discoveries will undoubtedly expand our understanding of the subconscious systems shaping human life. Advances in brain imaging, artificial intelligence, and computational neuroscience are already revealing previously hidden patterns of neural activity. These tools may one day provide deeper insights into how the brain generates thought, emotion, and awareness. Yet some mysteries may remain difficult to resolve completely. Consciousness itself, the subjective experience of being aware, continues to challenge scientific explanation. Even as researchers map the neural networks associated with awareness, the deeper question of why physical processes give rise to experience remains unanswered. What we do know is that beneath every thought lies an extraordinary network of processes quietly guiding our lives. The subconscious mind evaluates possibilities, stores experiences, predicts outcomes, and shapes emotional responses, often without the conscious mind ever noticing its work. The self we experience may represent the visible surface of a vast cognitive system operating beneath awareness. In many ways, the conscious mind resembles a traveler riding across the surface of a powerful current. The traveler feels the motion and chooses a direction, yet the deeper flow of the water determines much of the journey. Beneath awareness, the brain continuously analyzes information, compares past experiences, predicts future possibilities, and prepares actions that eventually rise into consciousness. So the next time a decision seems to appear suddenly in your mind, or a feeling guides you toward one path instead of another, it may be worth remembering that the process likely began long before you became aware of it. Somewhere within the hidden networks of the brain, an extraordinary system has already been working, drawing on memories, emotions, predictions, and experiences accumulated over a lifetime. And in that sense, the story of the subconscious mind is also the story of what it means to be human. Beneath the surface of awareness lies an intricate and mysterious system, one that has been quietly shaping every thought, every choice, and every moment of experience since the beginning of your life.